Right. Hopefully this is working. Yes, I think the audio is working. So if you're joining us online on YouTube, uh, thank you so much for joining us. This is the last edition of the RQI circuit. This is an online edition, and I guess that is going to work very similarly to the last one. So without further ado, uh, our first speaker here is Michael Good. So Michael, if you can start screen sharing for us.
Thank you, Rick. Thank you for having me, and thank you for the invitation. And I also appreciate your efforts to run such a nice circuit. So let me tell you that my talk. I'm super excited to tell you that about classical acceleration temperature, this CAT. I'm based in Astana, Kazakhstan. Right now, I'm in the U.S., but a lot of this work is done with some of my very good colleagues. Morgan is in the audience right now, Dr. Lynch, and we know a lot of connections between temperature and acceleration currently in physics. Probably the famous one through the equivalence principle is that of Hawking radiation for the Schwarzschild black hole, where G is the surface gravity of the black hole. And you can see that using SI units, that H bar here kind of signals the fact that Hawking used quantized fields. C is the addition of special relativity, and Boltzmann constant signifies that this is thermodynamics. Now, there is a flying moving mirror model, which has been well known since the 1970s to also be an analog for black hole evaporation. And it has a temperature too, where this variable kappa represents a scale, an acceleration scale that characterizes the trajectory, or the equation of motion of the moving mirror itself. It's also uses quantum fields and is thermodynamic and a relativistic effect. And then there is the infamous Davies-Fulling-Unruh effect, that of a uniformly accelerated observer in Minkowski spacetime who finds himself immersed in a thermal bath. So alpha here, you can see, is the uniform acceleration. So several different connections between acceleration or surface gravity and temperature. But the effect that I'd like to tell you about today is one that is actually classical. So it stands out a little bit due to that reason. And you can see it is the effect here is the temperature of an electron, or if you will, more precisely, the temperature of the photons emitted by an accelerated electron. The temperature here is proportional to the electric charge squared and kappa. And now kappa has a particular meaning in this context, where it is related very closely to the flying mirror, more so than the uniform acceleration of the thermal bath, and more so than the gravitational, surface gravity of the Schwarzschild black hole. So this kappa here, I'll tell you a little bit more about it, but suffice to say, it actually corresponds to the one single dimensionful acceleration scale, the parameter of the system, and we'll see it a little bit more clearly here in the trajectory. So this is not a uniformly accelerated trajectory like in the Unruh effect or the thermal bath of the uniformly accelerated Davies-Fulling-Unruh effect. This is a dynamic trajectory. It has time dependence. And a very simple way to express this trajectory is the inverse velocity here, where time is the coordinate time, r is a coordinate distance that's like a radius. It starts from 0 and goes to r equals infinity. C is the speed of light. S is the final speed of the electron. So it stays time-like in this Penrose diagram. You can see it's always below the speed of light. And kappa is the dimensionful acceleration scale. So it doesn't really have any meaning besides a parameter that characterizes the particular trajectory. So this is a trajectory that I'd like to just suggest to you as an ansatz. It's what I'm going to assume, and I don't want to justify it. I don't want to have to motivate it. I'm just going to say, please accept this trajectory, and let's see what happens if an electron were to move along this trajectory. And I think that you'll be excited to see what the result is. So to give you a little bit more familiarity with what the dynamics are like, it starts off at zero velocity. So it starts off at rest. So an electron moving along this trajectory would be completely still in the far past. But then around time equals zero, it shoots up with its velocity and goes to its final speed, s. This is pretty much a Heaviside step function description for the velocity, if kappa is large enough, or if the speed is fast enough. So the acceleration, the proper acceleration here is always positive. So it's always accelerated in the direction of travel. It never has deceleration in the opposite direction. It actually just gets less positive in the future. So it has some maximum, and then it falls down to zero in the far past and far future. So it's completely asymptotically inertial, a very physically realistic type of motion. Now, if you run this trajectory through, just like with the every chapter in every electrodynamics book, intro electrodynamics books, Jackson and Zangwell talks about moving point charge. It's been a staple for our understanding of radiation, especially with respect to synchrotron or Bremsstrahlung radiation. And you just turn the crank and compute the power distribution or the power. You can do this completely analytically, and you get some pretty simple results. Here you can see that when the electron's speed of beta is zero, that prefactor out in front causes the power to be zero. When the speed reaches s, the post factor here turns also into zero. So the power is zero in the far past and far future. So there's this time period where you have an emission of a lot of power, but then asymptotically you have no power. So turn the crank, solve for the spectrum using spectral analysis. This I omega represents the spectrum. It's the amount of energy radiated per color of the photons, and you can get a spectral distribution. And immediately one sees a very interesting characteristic on the right-hand side. You can see this Planck factor. This is a well-known Planck distribution that characterizes Bose-Einstein statistics of the photons. So we can integrate this over the solid angle, and the Planck distribution remains robust, and you get a spectrum, an analytic spectrum. It depends on the electric charge, E squared. It also depends upon this factor in parentheses, which depends on the final speed of the electron. So this is a one-dimensional Planck distribution from an accelerated electron. Now, one-dimensional meaning that it's not the Planck distribution that we see from the sun or from the universe or from your oven, but in fact, it is one-dimensional Planck spectrum, which does have some corresponding phenomena in the real world, namely, a resistor. It's been well known since 1928 that if you just have a wire in a normal room temperature room, that you'll have a current moving through it. And that current is white noise. It's called Johnson-Nyquist noise. And the electrons have a temperature. And it's a one-dimensional Planck distribution. So this is a real life thing. It's not to be looked on as some sort of artifact or anything. The one-dimensional Planck spectrum has been measured inside a circuit. So I can also say that the black hole is a one-dimensional Planck spectrum. So black holes radiate with 1D Planck distribution. So what's interesting is that if you take this, the color to be very, very red, super long wavelengths, and very, very small frequencies, this infrared regime, you get a constant. And it turns out this is the spectra for infrared spectra for all scattering events. And so there's a bit of universality in this result, at least in the infrared regime. And so you may also recognize that this is actually the spectra for the photons emitted by an electron during its creation from a neutron. So when a neutron converts into a proton and an electron, the electron goes accelerating away and gives off some light, some gamma rays. And that light has, to lowest order, this spectrum, a constant spectrum that's independent of frequency. And so we, me and my colleagues, decided to look at beta decay, where a neutron is converted into this electron, and check out to see if our spectrum, I omega, could characterize the color of light from beta decay. And it turns out, just very briefly and in a nutshell, this is the only slide I have on this, but I hope very, very much that our paper will come out very soon, maybe within a week or two, where we have taken our spectrum, this I omega, that's this one-dimensional Planck spectrum, and we simply plot it with the particles versus the color. And when we plot it, and then we also plot the data from free neutron beta decay using the RDK2 experimental data that was published in Nature and Physical Review Letters, we find very good agreement to statistical agreement. I believe the result is at least as good as a 3 sigma result. And we don't have to do any fitting of our spectrum to the data. In fact, we just simply plot our spectrum and the data agrees with it to uncertainties. So we have experimental confirmation that the radiation from an accelerated electron is indeed thermal and follows a Planck distribution, a one-dimensional Planck distribution. If you take that spectrum and you integrate over all the colors, you get the total energy, which happens to be the total energy radiated during beta decay. So everything is quite consistent. This is a classical picture here, right? I mean, beta decay is a quantum field theory result. It's a weak nuclear process, and we're using standard classical electrodynamics to describe the thermal emission that happens during beta decay. It's very impressive that classical theory could be so powerful here. But this, of course, is the lowest order contribution to the energy. There are higher order corrections, but those higher order corrections in most circumstances are extremely small, and they are negligible for our purposes. But to give you an idea, I believe this amount of energy, at least in some contexts, is 99.7% of all the energy radiated. So we can be pretty accurate with classical theory, at least to lowest order. So now that I've hopefully maybe stimulated or given you some interest in this spectral behavior for the electron, I'd like to motivate the trajectory itself through a very interesting mapping, a duality between the electron and the flying mirror. It turns out that if you have a flying mirror that moves along the same trajectory, you get the same energy, effectively the same energy. They only differ by a constant. In the mirror's case, you have h bar, and in the electron's case, you have the electric charge squared. So there's a deep connection between the flying mirror model, which is a 1+1 dimensional toy model, very low dimensions, very artificial, you might naively assume. And whereas the electron is an ordinary electron in 3+1. So, but it turns out that this mapping between the electron and the mirror, it works for all trajectories, at least asymptotically inertial ones. And Lamar power has an analog where the power is proportional to the acceleration squared. And the only difference here is by a constant, where h bar is effectively turned into the electric charge. It works for the Lorentz-Abraham-Dirac force, which is simply the jerk. It's a time derivative of the acceleration with respect to the proper time. It's in fact quite an incredible functional identity between the moving mirror and the electron. Now, this has been known for some time, at least to some extent, worked on by a 96-year-old man now, Vladimir Ritas, which we are in contact with, and he's very has been very committed to understanding this duality for the last 30 years, publishing paper after paper, and it, in my opinion, has not gotten the attention that it deserves. But you can see that there are several quantities that have a very easy to understand analog between the two. Not only the force, power, and energy, but the amount of particles as well. And the object that we're interested in is the temperature. So if you use stony units, say where a connection between temperature and frequency is understood with the scale of E squared, you get an analogous object for temperature. If you use our familiar Kelvin, it turns out the temperature of the electron is actually equal to the temperature of the mirror. So the constant here is in joules per second. It's this E squared versus H bar, and the difference between these two models is exactly 10.9. A factor of 1 over the 4 pi times the fine structure constant. So here's the difference between the Stoney scale and the Kelvin scale. So it really doesn't matter what constants you use. But what it does tell you is that to use Kelvin, regardless of whether you're using quantum ideas or not, H bar will make an appearance. So the H bar could be very misleading whenever you see it, because anytime you're dealing with temperature, the Kelvin is defined by H bar. You've got to use H bar if you want to use Kelvin. So it doesn't mean that it's a quantum effect. And if we use Kelvin, then we would also get the same formula as Hawking evaporation, flying mirror, and the Unruh effect with this H bar out in front. So that being said, I'd like to maybe say a statement of speculation where it could be that it might be possible through the equivalence principle, because gravity hasn't been quantized and the way we understand general relativity is completely classical. It could be that Hawking evaporation could be understood from a purely classical point of view. And using this model, we might be able to make some headway on this type of idea. So this type of direction here. So it could be that Hawking evaporation is a classical acceleration temperature effect. But nevertheless, that's speculation. So this model is classical, and I'd like to end this talk with just one statement on the dynamics of what kappa means. So if you take the object called the peel, or the local acceleration, or the effective temperature function, which is just the second derivative of the advanced time over the first derivative, you'll get an object that in a double limit of fast electrons' final speeds and late times, this peel equals the kappa. So this is it's not that nice, it's not that intuitive, and it's not that pleasing, but it is a connection between dynamics and the scale of the system. So you can see that, when you plot this peel, you get a nice plateau where the plateau is equal to kappa here in normalized units. So there is a connection between kappa and the dynamics of the electron. So in conclusion, I want to just say, if you're going to walk away from anything from this talk, I'd like to tell you that the thermal spectrum from an electron, it's one-dimensional. That's pretty interesting, just like a resistor, just like a black hole. And number two, there's a holographic duality between an electron and a mirror. So the mirror is in 1 + 1 dimensions, the electron's in 3 + 1. This is really neat. All the information of the mirror system can tell you everything you want to know about the electron system. So this is like a holography. And then the radiation from an accelerated electron has this temperature. So with that, I'll take back my time, and I very much appreciate your attention.
Thank you so much, Mike. Nice. So are there any questions from our Zoom audience? Yes, Morgan already has his hand raised. So please, Morgan, go ahead.
So one of the things that I really liked about this analysis is that it comes out as a one-dimensional Planck distribution, and that has some grounding in the kind of older literature in terms of this resistor. And so I was curious if you know, the fact that you're getting this one-dimensional noise, a Planck distribution noise in these resistors, is there in some way that just by chance that all these resistors that we've been making have some sort of analog horizon and some infrared in there, or is there anything that you can anticipate that would be some sort of an analog of a horizon that's creating this this one-dimensional distribution, but in resistors?
That's really good. That's a good question. So to think of the idea of a horizon in terms of the resistor, I haven't thought about it because, you know, I can't think of anything that comes off my head of how a resistor could have this horizon. But I have thought a little bit about the fact that they're both systems involving electrons, which is curious. And there also are both systems that appear to be important in the infrared. So the structure, the fact that the electron has no structure, the fact that all scattering processes in the infrared give the same spectrum, this suggests a type of universality. And I bet you there's clearly a link between the two systems in the infrared, and maybe by the fact that they're electrons. But as far as a horizon goes, that would be an interesting thing to investigate. Well, so there's not a strict horizon in this electron, at least from the idea that there are light rays that never hit that never reflect off of the electron or never hit the mirror. So it's not like the black hole horizon or a trajectory that goes to light speed. This actually is always time-like. So there actually is no horizon. So that's good that you remind me. So in fact, I bet you that it doesn't have to do with a strict horizon.
Good. It's interesting. Very cool stuff.
Yeah. Thanks for the question.
Thank you so much, Morgan. Thanks, Mike. So let's thank Mike again. And so thanks a lot for the talk. I guess that our next speaker is already here. So it's Maxime.
Yes, hi. Can you hear me?
Yes, perfectly.
Wonderful.
I can, Maxime. Thank you.
Great. Thanks for the talk. Okay, so can you see my screen as well?
Yes, we can see your screen, but we can also see ourselves. It's not really an issue.
Yeah, it's going to... I don't know.
It's also not full screen, that's all.
Yeah, I don't know why. There we are. All right.
Amazing.
Cool. So normally you don't see yourselves anymore, and you see my full screen.
Yes, this is perfect. Thank you so much. All right. So our next speaker is Maxime Jacquet. Yes. Maxime is going to talk to us about superradiance and fluids of light. So please, Maxime, the floor is yours.
Thank you very much for having me, and thank you very much for organizing this last session. It was nice to follow the RQI online throughout. It's nice to see the whole community, even though we cannot always meet. I prefer meeting in person, but it's nice that we have this thing online. Today, I'm going to tell you about work that we are doing at the moment at Laboratoire Castres-Bruxelles. It's experimental work in collaboration with theorists at Louisiana State University in the group of Ivan Agulot. And then the main person who is cracking on the numbers is Adria Delhomme, who is a postdoc. Whereas in the Laboratoire Castres-Bruxelles, I work on the experiments with PhD students Kevin Falk and Kilian Guerrero. The topic of today's talk is really to tell you about superradiance, and I thought I could give a brief introduction on what I mean by superradiance very specifically. And this is all summed up in this picture that's on the top right of the screen, where we see that we have a potential with some maximum somewhere. It's a spatially dependent potential, but it's independent in time, so it's a completely stationary process that we are looking into. And we imagine that we have wave packets that can scatter on this potential, so they can be coming from the left or from the right. They are those red wave packets, and we wonder what's happening to the amplitude of the wave packets that would be reflected or transmitted, and these would be the blue ones. And usually when we do that, we write a Schrödinger equation, and then the quantity that is conserved during this scattering process is the probability. And the fact that the probability is conserved tells us that the modulus squared of the transmission and reflection coefficients add up to give 1. If, however, instead of a Schrödinger equation, we write something for a bosonic field theory, like a Klein-Gordon equation in Minkowski spacetime, or in Schwarzschild spacetime, or in a Kerr spacetime, then it's not the probability that is conserved. Instead, it's the charge. And the charge is a bit more special. It involves the special derivative of it involves the special derivative of the temporal derivative of the field, as well as the field itself, or rather the conjugate momentum of the field and the field itself. And because this is the conserved quantity and it can be negative, then it's really the modulus of the squared modulus of the transmission and reflection coefficients that adds up to 1. And we see in this equation at the bottom right of the screen that we can have conditions where t squared is greater than 1, provided that r squared exceeds 1 as well. In which case, we can have really amplified reflection at the cost of having some transmitted light into a negative norm mode. And that's really what the Noether charge tells us. It tells us that as soon as we have negative norm modes that are available in the system and we have a way to scatter energy into them, then we can have amplification of energy when we have scattering of a wave packet. And that's encrypted in this B matrix, which is a matrix of complex coefficients. And if that matrix is not unitary, then we have amplification. And very generally speaking, this amplification is superradiance scattering. So one very famous example of superradiance scattering is rotational superradiance, as described by Zeldovich for a rotating cylinder, and that also exists in black holes. It's connected somehow to the Penrose effect. And that's what I want to look into today. I want to look into rotational superradiance in the laboratory. So I want to run an experiment where we see this effect. And the way we set up this experiment is that we use the methods of analog gravity, where we have a fluid with a certain velocity that's proportional to the gradient of its phase, the spatial gradient of the phase, and a speed of sound. We look at the acoustic field in that fluid. And the wave equation for the acoustic field in that fluid has this complicated shape that's in the center box, but it can be very easily written out in a simpler form by using the covariance notation and writing out a metric tensor whose components depend on the relative speed of sound and of the fluid in the experiment. And so if we have a flow that is inhomogeneous, such that somewhere we have the speed of the fluid that exceeds the speed of sound, then we will have some scattering that will occur in a purely stationary time-independent space-time. And the acoustic field then plays the role of the scalar field. It can be even a massive scalar field. That's what we have in our case, on a curved space-time. And this was all formalized by Unruh and Visser later on, and is the basis of analog gravity. So how does this work? Really, in the experiment, we take our metric tensor and we can have various scenarios. So the very famous scenario is you have a fluid that's just propagating in one dimension. In space, it goes from sub to supersonic. At the point at which the flow velocity of the fluid exceeds the speed of sound, we have an acoustic horizon. If we generalize this to 2 dimensions with rotation, then we have an azimuthal velocity as well as a radial velocity. Where the radial velocity exceeds the speed of sound, sound waves are trapped. We have a trapped surface that's an acoustic horizon. A bit further out from that surface, where the total velocity of the fluid exceeds the speed of sound, we have a static surface, and that's an ergo surface. And that's the surface that's of interest to us today. In the geometry that I'm going to show today, we have purely rotating velocity and no radial velocity at all. So we form an ergo surface and no horizon. And I'll explain later why this is super interesting to us. So the way we do the experiment is with these microcavity exciton polaritons, or polaritons, really, which I'm not going to explain the physics of in depth today, but they are essentially photons that come from a laser that are dressed with material excitations that live in a plane. So it's a purely planar geometry. The way we dress the photons with excitations is that we confine the photons in a microcavity, a Fabry-Perot cavity. They interact in that cavity with the semiconductor electrons that are those excitons, and they found and they form bound states, those excitons, that strong couple to the photons. And via strong coupling to the photons, the cavity photons that already have a mass from confinement, an effective mass, acquire also the ability to interact non-linearly. So in the plane of our microcavity, the polaritons that are the result of the strong coupling of the photons with the excitons are bosonic particles that are able to interact with one another via some non-linearity of type K3. And their dynamics in the plane is described by the Grosspitaevsky equation. It's a type of nonlinear Schrödinger equation that's in the bottom box. It's got a term for the kinetic energy. We see that the kinetic energy of the fluid, the ensemble, comes from the mass from confinement of the photons, whereas the nonlinear interactions are all in Gn, and G is the interaction constant of the electrons. It's the contact interaction of the electrons. We also have, of course, the fact that we send photons in the system. That's our pump term, and at some point, the mirrors being imperfect, the photons exit the system. That's our gamma term. Those are the losses. So we have those bosons that have a limited lifetime. It's of the order of 10 picoseconds in the experiment. It's going to come back later, this 10 picosecond number. So if you want, I send photons on the sample. The photons interact with the electrons. They form those excitons. They strong couple to the excitons, and together they form those polaritons. They live their life described by the Grosspitaevsky equation. They de-excite, and the photons come out. And I observe those photons. In the detection, I observe the photons, and by measuring the intensity of photons that I get, I have a relationship to the density of polaritons in the cavity. By measuring their phase, by interferometry, I have access to the phase of the polariton field. So I can do in situ measurements that are totally non-destructive, just thanks to the driven dissipative dynamics of my system. And that's incredible because I can also shape the beam that I send. And here we have the results of the experiment that I'm going to come back to later. But I can form a vortex of light that creates a vortex of polaritons. And in that vortex, I can have an ergo surface, and I can study rotational superradiance in the experiment. So the general idea here is to create a vortex. So that's a purely rotating system, or a maelstrom. That's a rotating system with some radial velocity. In our case, we have a vortex. And in the experiment, what we would want to do is to look at what happens, what's the fate of an excitation that would scatter on the ergo surface. I can send a probe to observe the amplification, or I can let the quantum vacuum scatter at the surface. The two work in the experiment. And then what I can do is, because I have access to the entire field, to commuting observables, I can measure quantum correlations across the ergo surface. I can see whether there is entanglement that's generated by the process, and I can even see, say, if I add now a horizon, I can see how this perturbs the entanglement created at the ergo surface and so on. So all this builds up on work that was done in the group of Silke Weinfurtner in Nottingham, where they observed rotational superradiance in a classical fluid. In our case, the fluid is quantum. And they observed some other phenomena that are linked to those vortices, such as the ring down and also some sort of like back reaction. We are first and foremost interested in rotational superradiance in the experiment. So the experiment looks like this. I have a laser, that's my TISA, titanium sapphire. It's sent towards the sample in the cryostat. And on the way, I pick up some of it to make a phase reference for my interferometry to measure the phase. But I also have the light of the laser scatter on a spatial light modulator, this SLM, spatial light modulator. It's a screen of liquid crystals that I can orientate the way I want to imprint a phase on the light beam. So I can that way create my vortex. The two telescopes that are the pairs of lenses that are highlighted in green image the plane of the spatial light modulator in the plane of the cavity. So I have the phase of the spatial light modulator directly imprinted on the plane of the microcavity. That's my all optical control. And then the light comes out and I observe it in real space where I do the interference, and also with a spectrometer to observe the spectrum. So let's look a bit at the light vortex before we create polaritons. So I create an image on the plane of the spatial light modulator, and via and that phase is just this function here, C over R minus D over R, and we can see how it changes as a function of the C and D parameters. So, for example, the C is the circulation. So it's whether I have convergence of my beam or not, whereas D is the number of phase jumps that I will have. If you want, it's how many. Sorry, it's the other way around. D is the drain and C is the circulation. So C is how many phase jumps I will have, and D is the drain. And we see that as we increase D, the phase jumps, they become more and more curved. That's the signature of a drain. But I can also create beams in which there is no drain at all, D equals 0. And there we see that I can get a number of phase jumps, and these phase jumps will create a circulation that will create a purely azimuthal velocity. So now I send this light vortex in the microcavity. It interacts with the electrons, creates the excitons to which it strong couples, creates the polaritons. And I measure the light that comes out of the cavity, and this is an experimental result now. So on the left, we have the intensity of the light that comes out of the cavity. On the right, we have the phase. The intensity, as I said earlier, is directly connected to the density of polaritons in the plane of the microcavity, and we see that it assumes an annular shape. That's typical of Laguerre-Gauss beams. So that's a proof that we have created a vortex. And indeed, if we look at the phase, we see that we have a number of jumps in the phase. Here, I think 15. So we have 15 jumps in the phase. Of course, in fact, there is unit circulation. It's just that I have 12 quantized vortices at the center of my vortex. 15 quantized vortices at the center of my vortex. So we also see that the phase jumps, they are relatively straight. There is not much curvature to them, which seems to indicate that there is very little, if not at all, radial velocity. And indeed, if I do the analysis of that mean field data, I obtain the speed of sound via the square root of the density. That gives me the red curve on the right-hand side. That's decreasing from large radii to short radii. Whereas the radial velocity in green is on average 0 and very close to 0 everywhere. While the azimuthal velocity, which is the total velocity because the radial velocity is 0, has a 1 over r behavior. It grows as 1 over r from large to short radii. At some point, this azimuthal total velocity crosses the speed of sound, and by definition, that's where I have an ergo surface. So experimentally here, I am showing you a stationary state of a quantum fluid where we have an ergo surface. And we can ask ourselves, okay, so what do the modes of the acoustic field look like in this situation? So we can resolve the Bogoliubov dispersion relation here in calculations, soon in experiments. Outside of the ergo surface, where the flow velocity is lower than the speed of sound, we see that we have a black branch at positive frequencies and a red branch at negative frequencies. But on the right-hand side, I write the Noether norm. I can tell you the black curve is positive norm modes, the red curve is negative norm modes. If now the flow goes supersonic, we are inside the ergo surface, in the ergo region, the negative norm modes are pulled by the Doppler effect. They are pulled to positive frequencies. So we have negative energy modes that are available, meaning that we can do superradiance scattering, right? This is a stationary system. We are in the stationary state. We have positive energy modes outside of the ergo surface, negative energy modes inside of the ergo surface. They share a common frequency. We can have superradiance scattering. And that's very nice. I mean, that's the experiment we want to run. But here, we have to ask ourselves the question, how is it possible that this is stable? I mean, if we think about it, there are always quantum vacuum fluctuations in the system. And I'm telling you that I can have superradiance scattering, but that there is no horizon. So there is no one-dimensional surface or two-dimensional surface that's going to take the negative energy modes out of the system. So here is how, with this quantum fluid of light, we can create a stable ergo surface without a horizon. So with new dissipation mechanism. If you want, the group velocities that we are talking about, they are roughly the speed of sound. They are of the order of 1 micrometer per picosecond. That's the red curve on the top right. Whereas the lifetime is of the order of 10 to 15 picoseconds. What this means is that the mean free path of excitations in the system, be they Bogoliubov excitations or quantized vortices, is of the order of 15 micrometers. And what we see is that the density, which is proportional to the square of the speed of sound, decreases very fast inside the ergo surface. In fact, at about 15 micrometers radius, the density is of the speed of sound is of the order of 0.4. That's a very small density where we don't have nonlinear interactions anymore. Everything that is at radii below 15 micrometers, in fact, has no physical meaning whatsoever. It's just noise in the data. So here in this experiment, if you want, sort of like 15 micrometers inside the ergo surface, we reach a point at which there is no more density, so at which there is no more Bogoliubov excitations, no more acoustic field. And so the negative energy waves disappear. They are taken out of the system by the intrinsic dissipation of the fluid. We have this microcavity, these intrinsic driven dissipative dynamics that allow us to pin the phase of the entire fluid with the pump and to ensure that it remains pinned and to reach a stationary state just because we have dissipation. So that's how this works. Now in calculations, Adrien Delhomme, he calculated that if we look at the vacuum fluctuations that scatter at the ergo surface, and we add some realistic amount of thermal noise in the system, we have thermal noise in our system, of course, like in all experimental systems, we can still get some degree of entanglement that's quantified by the logarithmic negativity, here shown as a function of frequency. So we can still see some entanglement. So that's very nice. That's really the experiment that we want to run now that we have this stable ergo surface. We want to look on either side of the ergo surface, measure phase and intensity correlations and anti-correlations or other commuting quadratures. And we want to see entanglement that will be generated by the scattering of vacuum fluctuations on the ergo surface. Okay, so I think I've reached the end of my talk and the end of my time today with you. I've told you how we can run experiments with polaritons, those bosonic quasi-particles with a limited lifetime, and how their limited lifetime allows us to create stable ergo surfaces. I've shown you experimental data on that, which is very nice for us. You can find the experimental data in this arXiv paper that came out in October. Hopefully soon it will be published as well. And I've also shown you some preliminary results of calculations where we have looked at the logarithmic negativity. So it tells us that we can see entanglement in the system even though we have some finite temperature. We have ideas of how to increase the degree of entanglement in case the temperature is higher than what we estimate. So this is a very promising system here to look at superradiance without interactions with the horizon, but then we can switch on the horizon, we can increase the drain in our system all optically, and then we can look at the interplay between Hawking radiation and superradiance and see how this modifies entanglement, which happens in all black holes, but we cannot really see that there. So I think these experiments in that sense are very promising to shed light on some open questions in quantum field theory in curved spacetime. And with this, I thank you very much for your attention.
Thank you so much, Maxime. Let's thank Maxime for this talk. Unfortunately, you already ran a little bit of time. If there is one question from the, that's okay. If there's one question from the audience, okay, Morgan, try to be brief, please.
Okay, so I guess I won't even say a question. I'll just say I wasn't aware that you guys had a system where you can use an SLM to imprint on the essentially on the wavefront, in a transverse sense. I think that these things are probably going to be a game changer. I mean, just as a simple example, you can make an airy beam with those things and make a self-accelerating polariton. I mean, you can basically any quantum field theory in 1+1 dimensions you can make by phase imprinting it with this thing.
Yep.
And that's I'll just leave it at that. That's a game changer. That's amazing.
Thank you very much for the comment. It's very nice to hear.
Yeah, it's really good.
Thanks.
That's great. Thank you so much, Morgan. Let's all thank Maxime again. And
Thank you very much.
No worries, no worries. Thanks for joining. Thanks for the talk. Okay, cool. So now we head to our next speaker, who is Elder Costa. Elder, can you try unmuting and speaking just to make sure that everything is working, that the audio is going well?
Yes, yes. Can you hear me?
Yes, amazing. Can you start screen sharing?
Okay. At this moment.
Right, we can now see your screen. Do you want to make it full screen? Perfect, amazing. So the next speaker of today is Elder Costa, who'll talk about quantum coherence of a uniformly accelerated detector. Elder, you have 20 minutes, including questions, so feel free to use this time. Floor is.
Oh, okay. I'd like to thank you for giving me an opportunity to talk at RQI circuit online. My name is Lawler from Piauí, Brazil. Today, I'm going to talk about quantum coherence of a uniformly accelerated detector. Here's my collaborators, Pedro, Irisma, and Olympio. The purpose of these presentations is to show you the loss of coherence by Unruh effect in the quantum interference. In particular, I will show the behaviors of wave particle properties and the Unruh effect. Okay. Quantum coherence is a fundamental concept in quantum physics. It refers to ability of a quantum states to meeting its entanglements and superpositions. However, coherence is a fragile property. It can be easily disturbed by interactions with the environment, for example. This process is known as decoherence. Recently, several papers have studied quantum coherence and relativistic contexts. Let's see a few then here. In particular, in this coherence, in this reference, according to the authors, the Unruh thermal buff causes the coherence and destroy the properties of the uniformly accelerated Unruh DeWitt detectors. So, in order to investigate the wave particle duality of a uniformly accelerated qubit, we consider the quantum scattering circuits conformly illustrated in theory. Okay. And then quantum scattering circuits involving controlled interactions between a single qubit, the probe qubit, and the system of interests, quantum fields. Here, the coupling between the detector and the quantum fields modify the interference patterns. In this context, the scattering circuit can be used by estimating the Unruh temperature and the loss coherence induced by Unruh thermal growth. Let's see how its setup works. Suppose initially that systems probe qubit and the plus and the field is prepared in the state given by product state. Okay. And then the action of the first Hadamard gas transforms the qubit state to the states and these superposition states. Okay, the probe qubits is linearly accelerated and decoupled to a massless scalar field. This coupling is described by U operator. Here, we consider the weak coupling regime, where the U operator given by this expression and the leading order and the first perturbations theory. Okay. In addition, the phase shift is introduced. Okay. See if the qubit is the STED state, okay, and the U operator induced by following transformation in leader order. Okay. Finally, the operations of the Hadamard get the final states of the system region. Okay. And then the reduces dense matrix of the qubits is given by these expressions. Okay. Note that the diagonal terms corresponding the probabilities to measuring the detector and ground states. Okay. Probability given by PG and the probability PE. Okay. And then off-diagonal terms encode information about quantum coherence of the system. Okay. So the Franging visibility for interference patterns is defined by difference expressions. Okay. The maximal and the minimal values of the probability AG occurs when the alpha equals 0 and the alpha equals P. The visibility is given by equations. Okay. And here we plot in the visibility of the qubit as a function of the accelerations. We observe that when the accelerations increases, the visibility decreases monotonically. This indicates that the loss of coherence. In this paper, we find the relations between the Ullmann temperature and the visibility. Okay, is given by these equations. Okay, now in order to obtain which way informations, we removing the second Hadamard from the interference setup illustrated previously, and we including two detectors, okay, detector A and the detector B. Detector A measures the qubit and ground states, while detector B measures qubits and the STED states. Choose the which way informations can be stored and the internal states of the qubit. So the probability of finding the qubit and the ground states is given by expressions, and and then we have the probability of find the qubit in the steady state. Okay. Page informations is quantifying by the difference between the probabilities WA and WB. Okay. This is a normalization factor. By using these expressions, we find these results. Okay. So let's to explore the behaviors of wave particles duality under the Unruh effect. For this, let's to analyze the complementarity relations. The complementarity relations is given by this inequality. Okay. Not that the equality is satisfies when both the qubits and the field are in a pure state. Okay. And this figure is, we plot the behaviors of visibility, page informations, and the complementarity relations as a functions of the accelerations. It shows that the visibility, page informations, and complementarity relations decreases with increases accelerations. This suggests that in regimes of high accelerations, the Unruh term above has a some impact on its wave particles properties. For very high accelerations, the complementarity relations, blue plot, indicate a maximally mixed states of a probe qubit. In this case, no informations about the wave and the particle aspects the qubit can be obtained. This lack the knowledge about the probe systems is due to another quantum properties, namely quantum entanglement. And in the other words, the qubits and the scalar fields becoming maximal entanglement, and the information about wave particles properties is being shared with the quantum field. Okay, and this other figure, we can see that the visibility and the complementarity decreases as the interactions time grows. In contrast, the page informations approach its maximal value for a long time iterations. Okay. So, all findings suggestions that the creations and the particles by the accelerations serve as the environment of the qubits, leading to a loss information about the wave and the particle aspects of the qubits inside the interferon. So let's me summarize the case points. First, the interference partners is modified by the Unruh effect, and the interference, and the Unruh radiations affects the wave particles properties of a uniformly accelerated qubit, and then the Unruh effect disturbs the internal states of the qubits, leading to loss information about the wave particle duality. Thank you for your attention.
Thank you, Elder. Thanks a lot for the talk. Do we have any questions from the audience? Okay, if not, I can ask a question while people think about it. So Elder, in your plot, you're plotting the acceleration at some point, right? You have a plot which is a function of acceleration, right? So in that plot, you don't have the units there for the A. Which units are you using in order to plot the all of the parameters that you're interested in?
We're using the natural unities. C, H barra equals 1. Okay.
All right, I see. There's no other scale of the problem that you could use as a scale in this case.
Yes. No, no. I don't see no problem in scales. In scales units. Okay.
Fair enough. There's no problem. It's just sometimes it's good to also use other parameters of the problem scales, but that's perfect. So if there are no other questions, let's thank Elder again. So thanks for your talk, and we can move on to our next speaker, Barbara Šoda. Barbara. So, amazing. Can you unmute yourself and just so that we can make sure that we can hear?
Yeah, can you hear me?
We can hear you. Perfect. Amazing. So I guess that without further ado, the next talk is going to be delivered by Barbara Šoda, and she'll talk about model for emergence of spacetime from fluctuations. So please, Barbara, floor is also all.
Thank you. Can you see on the right? Can you see yourself? Or okay, that's good. Okay, so today I'm going to, in this short talk, I'm going to talk about this quantum gravity model. It's a paper that I wrote with Markus Reitz and Achim Kempf, and it was recently published. So I think in this series of talks, Achim already talked about the conceptual background of our model. So because my talk is going to be short, I'm going to jump in straight into technical details. So let's start. So the idea is to build a quantum gravity path integral, and the first point in building this path integral, well, we started with this unusual formula, which we call Hawking and Gilkey formula. You can find it in one of Hawking's papers where he cites Gilkey. So this formula, imagine there's a manifold, and then there's a Laplacian operator acting on that manifold. This formula relates the number of eigenvalues of the Laplacian below some UV cutoff to a gravitational action, which is the right-hand side of the equation. So we have an equality between the number of eigenvalues and some gravitational action. And this gravitational action looks like Einstein-Hilbert action with higher order corrections. And so we can use this formula to formulate the gravity action in a different way than usual. So we will, using the right constant of proportionality, we will say that the gravitational action is equal to mu, which is this constant, times n, where n is the number of eigenvalues of the Laplacian. And that's the representation of the gravity action in the eigenbasis of the wave operator. Alternatively, we can also write the action basis independently as, again, mu, and then mu multiplies the trace of the identity operator. So we are interested in having a basis independent way of writing actions for gravity and later also for matter, because we want to go beyond space-time representation, and we will sum over all kinds of contributions to the path integral. I'll talk about that later. And just one remark is please notice for later reference that the ratio between the number of eigenvalues and the volume is some constant plus higher order corrections, and that's going to be important later for a consistency check. Okay, so in addition to a gravity action being represented in this odd way where we say that it's proportional to the number of eigenvalues of the Laplacian operator, we are going to also add free bosons to the path integral. And so the way we write down the boson actions, you can imagine first writing it down as the Klein-Gordon action, but then rewriting it as it's written here in a basis-independent way. So this is so we have a sum over the number of boson species, and then trace over the Laplacian operator plus a mass term, and the state operator. So imagine that you perform the trace in the position eigenbasis, and then you'll get the usual Klein-Gordon action. Okay, and because we've written it down now in a basis-independent way, down there you see that we can also write it in a preferred eigenbasis of ours, and that's the eigenbasis of the Laplacian. So then the action becomes represented as the eigenvalues, the lambda n's, the eigenvalues of the Laplacian, and phi n's, the components of its eigenvectors. And similarly, we also add free fermions to the model, and we basically add free fermions as the square root of the free boson. So the eigenvalues of the Dirac operators are the square root of the eigenvalues of the Klein-Gordon operator, and then we have the Grassmann numbers here. Okay, and so in the beginning we assumed that all the masses of all the species are the same, but then we'll talk about also when we have non-trivial spectrum. So we take all of these actions that are just introduced, the gravitational action, boson action, and fermion. We put them all together, and we put them inside the path integral. So that's this e to the minus beta s term in the path integral. To the right of that, I don't know if you can see my cursor, but there are some normalizations that you can ask me about. It's not so important. Sorry. Oh, you can see it. Okay, good. And then what we do in this path integral is we sum over all the possible values of n. So that's all the possible numbers of eigenvalues that the Laplacian has. And then we are also summing over all possible eigenvalues and all possible components of the eigenvectors. So that's our path integral. And one advantage of this path integral is maybe it looks complicated, maybe not, but in fact, you can actually compute it analytically. And so when you calculate it, it looks, path integral looks like something like that. It's not very complicated. And because we have an analytical expression for it, from it, we can now calculate some observables. And the first thing we can calculate is the effective dimension of space-time. In order to calculate this, the dimension, we use while scaling. So, okay, so first of all, because we can calculate the path integral, we can also calculate the scaling of the density of eigenvalues. And then we use this eigenvalue density to plug into the while scaling formula. Now, if you don't know what the while scaling formula is, so the while scaling formula relates the behavior of eigenvalues as they asymptotically go, towards high values. It relates their behavior to the dimensionality of let's say the box that they live in. In this case, it's actually the space-time dimension. But in quantum mechanics, you can imagine having some oddly shaped box, and you can look at the spectrum of the Hamiltonian there. So the spectrum for large wavelengths will depend on the shape of the box, but then as you go to higher and higher wavelengths, the shape of the box starts being irrelevant, and the only thing that matters is the dimension of the box. So here we have the same behavior. Basically, we say for large eigenvalues, the only thing that matters is space-time dimension, and from that we infer what the effective dimension is. Okay, and the result in the end is that we relate the effective dimension to the number of fermions and bosons in space-time. So this is the formula 2 plus NF minus MB. It has this curious behavior where it looks like the presence of fermions increases the effective dimension, and the presence of bosons decreases the dimension. So it has, physics-wise, it has similar behavior to a neutron star. And so the previous result, the simple result where it's just a simple formula 2 plus NF minus MB, that's valid for a trivial spectrum where all the masses are the same. If we introduce a non-trivial spectrum, then we have an energy dependent effective dimension. So we can have things happening like the effective dimension is higher at lower energies and smaller at higher energies. I think in this example, we just show that it's possible for some choice of number of fermion and boson species and a choice of the spectrum to have at lower energies a 4-dimensional spacetime, and then which becomes 2-dimensional spacetime at higher energies. And so this is just, we just made a convenient choice to make this happen in the model. It's just, it's reminiscent of various quantum gravity approaches where people argue that the dimension of spacetime reduces to 2-dimension when you go to high energies. Okay, so another observable that we can calculate is the expected number of degrees of freedom. So that's the expected size of the Hilbert space defined by the the eigenspace of the Laplacian. So we can calculate that. And additionally, we can calculate the effective volume of the spacetime. The way we do that, well, so we can not only calculate the eigenvalue density that I talked about earlier, we can also calculate the expected spectral gap in let's say analogous way. And so once we calculate the spectral gap, then we can relate it to the effective volume of spacetime because it's related to the gap. It's inversely proportional to the gap. And so we can actually find a nice expression for the volume. And so because we have the expected number of degrees of freedom and expected volume, then this allows us to perform a consistency check. So if you remember at the beginning, I mentioned how from the Hawking-Gilkey formula, which is a classical formula, it's true for a Euclidean manifold. You can just quickly show that the ratio between n and v is a constant plus some higher order corrections, and then that's the classical formula. And then we use this classical formula and put it inside the path integral, and so we made everything quantum. And now after we performed the path integral, we have a new n and v, and we wanted to see is this ratio still behaving the same way? So does it work out well that the quantum result is classical result plus corrections? And it does work out well. So it's some sort of a consistency check where we find that this ratio is still constant plus corrections. So in some way, you can think of this also that so inside our path integral, there are contributions which are representable as manifolds, but there are also contributions that are not representable as manifolds. And you could ask yourself, well, what kind of contributions dominate? And this result indicates that manifold-like representations are a big part of the path integral. Okay, I don't know how I'm doing with the timing, but in summary, we performed a path integral using unusual variables of the eigenvalues and the eigenvectors of the Laplacian. We added also free fermions and free bosons to the path integral. Because the path integral was easy to calculate, we could then calculate the effective dimension and volume of emergent spacetime, and we could study how these observables are dependent on gravity and the fermion pressure acting against a boson pull. So we found that there is an energy-dependent space-time dimension when the mass spectrum is non-trivial, and we found that maybe I didn't comment that when I was showing the plot, but we found that often there is it seems that the good approximation, so the good representation of the correlations that we find is like almost smooth spacetime, which you can show because the effective dimension is an integer. And finally, we show that a consistency check, which demonstrates that the quantum calculation is the classical result plus some correction. So we show that this consistency check is okay. And that's all.
Thank you so much. Let's thank Barbara. Nice. Are there any questions from the Zoom audience? Because I have a couple, if not. And all right. So Michael, please feel free to unmute and ask.
Hello. I have a question about your action. Oh, actually, it's more about your dimension. Yes, this page. So, is there a supersymmetry in this problem? Does it like in this limit that you where this effective D you get this result?
We didn't assume any supersymmetry, so we assumed that there is some number of
questions emergent supersymmetry.
I don't think we see something like that.
I guess I've studied a number of problems which are supersymmetric, and there's a within index which ends up being the number of fermions minus the number of bosons. And so, just looked familiar to me.
Right. Yeah. So I don't know much about that, but what I can say is that in this model we put these numbers in by hand, and we don't get any dynamics of these numbers, right? The only dynamics that's happening is when you introduce a non-trivial spectrum, then the dimension of spacetime can change. As you unlock new particles, then this can change the ratio. This can change the number of fermions versus number of bosons, so it can change the effective dimension. That's the only thing we see. But actually, in follow-up work, this is something that we want to do, is not have these numbers plugged in by hand, but also have them be one of the observables that we can calculate. So we'll see what happens in that work.
Right.
Thank you.
Amazing. Any other question from the Zoom audience? Okay, so if not, then Barbara, these results that you've shown, are they valid only for the Euclidean case, or do they also apply for Lorentzian manifolds? That was not 100% clear to me.
These are, maybe I just mentioned in the passing, I should have mentioned it more clearly. So these are Euclidean results. And the reason it's Euclidean is that we use this Hawking-Gilkey formula that's derived in Euclidean manifold.
Yeah, that's the impression that I had. And like, is there any analogous thing that could also be applied for the case of for Lorentz signature, or do you think that the generalization would be not straightforward?
I think it's not going to be straightforward, and yeah, I'm not sure. I don't want to say anything wrong, but usually even mathematical results, you have a lot of results in Euclidean signature and then not that many Lorentzian signatures. So for us, this was kind of like we just took a formula that already existed and then we plugged it into the path integral and everything works out. And then as far as I know, there is no analog of that for Lorentzian.
I see. Well, thank you so much. So now let's thank Barbara again. Nice. Thanks for your talk. That's a very interesting work. And our next speaker is already, of course, here. Wait 1 second. Let me just organize one thing here. Nice. Okay, Michael, we can clearly hear you from last time, so that's great. Can you start screen sharing now?
Sure.
Amazing. I think we can see pretty much everything. So the next speaker of today is Michael Lawler, and he will talk to us about realizations of under-the-width detectors in tabletop experiments. So please, Michael, the floor is yours.
Thank you. It's a pleasure to be here. I really think this RQI circuit is a wonderful way to build community, and I'm excited to be part of it. And I hope that through my talk that that we have a lot of questions in this area, and we're excited that there's such a large community of people who are interested in similar topics. So I will talk about realizations of under-the-width detectors in condensed matter settings. That's what I mean by tabletop experiments. And we're interested in the question of whether we can make qubits talk to each other through electrons communicating between the qubits. And in order to help think about this problem, I've done some simulations. So the picture on the lower left is a picture from my simulation, and then the simulation takes place in one particular concrete setting, but I'll then branch out and talk about several other concrete settings. Then I will end with a discussion about what we're doing at Binghamton University as far as implementing some of these, or at least one of these settings, and that's I'll get to that. So several years ago at Binghamton, we were responding to one of the U.S. Department of Energy's solicitations. This one was on next generation quantum systems, and at Binghamton, some of us in the team were pretty good at making quantum dots, which could host a qubit, a spin qubit. So it's just a lump of material, and you put some spin impurities inside. It's a well-established technology. And we were wondering how we could use these quantum dots to build next-generation quantum systems. And we thought, what if we could exploit the fancy properties of topological materials in order to help these qubits communicate, in order to progress quantum information science. And topological materials, I'm not sure how many of you are familiar with them, they're fancy materials which have special properties that enable electrons to not scatter easily off of impurities. That you might normally give up the notion that electrons could be used in a material, could be used to help communicate quantum information because they just scatter a lot. That's what resistance is and resistivity is. But topological materials have a very special property that helps them avoid scattering off of these impurities. And so an example, the classic example is the quantum Hall effect, which is basically what we use. This effect is what we use to define resistance in a material. And here's an example where the Hall resistance is got a quantized value, but the longitudinal resistance is 0. So that 0 resistance is not scattering. Things are not scattering. And maybe we could use that effect to help qubits communicate in materials. And unfortunately, our proposal was not funded, but we wrote up a lot of our ideas in this paper, Design Constraints for Unread DeWitt Quantum Computers, which is on arXiv from last year. And it's in collaboration with a chemist, John Marone, who really helped us on the experimental side, and Eric Aspling, who's the next speaker in this sequence here. So you'll get to hear from Eric more about some of these things. I won't present everything. I won't present. Actually, what I'll do is I'll focus mostly on the experimental settings, and I'll leave more of the theoretical aspects to Eric's talk. So what we thought about, and it's something that we could have actually grown at Binghamton University, is to grow a quantum well where we can trap electrons in a 2-dimensional layer. And we need a special quantum well, this mercury telluride, cadmium telluride quantum well, where these electrons have very special hopping properties so that they give us this topological material that I just mentioned. And it was first proposed that it would do this in 2006 in a paper by Bernavik, Hughes, and Zhang. And that was really this material was actually the first topological insulator material. I don't know if you've heard of topological insulators, but it made a big splash back in 2006 that our theory of insulators was incomplete, and that there are 2 classes of insulators, the sort of trivial, topologically trivial, and topologically non-trivial. And this paper proposed the first real material to exhibit a topological insulating behavior. So here's my simulation. What I was able to do is I could basically create this image where every pixel in the image is an atom. And I take these rules for how these, and on each atom, I allow there to be, I think there ends up being 4 states. And for the electrons, the electron can take on 4 different states. Maybe you can think of it as 2 different orbitals on the atom. And then there are this model for how the electrons hop around in mercury telluride. And without turning on interactions, so free Fermi gas, I can simulate a very large system. 226 nanometers is the horizontal, and 130 nanometers is the vertical axis. And what I plotted here is the local density of states, which is just the projection or the wave function of the first 10 eigenstates summed over the sum of the first 10 eigenstates. And it just gives you a sense of where are the electrons in this low energy regime. And what happens is the electrons are not present in the bulk of the material, and they only live on the edge of the material. That's what I want to do, on the edge of the material. And in fact, we can even plot, here's like the wave function. It decays exponentially into the edge, and it has a fairly sharp intensity on the boundary. And now here's where maybe we started to get connected with Unread DeWitt detectors that, in one dimension, electrons obey the Dirac equation. So this boundary of this system, there are Dirac fermions that are going around the boundary. Actually, in these topological materials in general, those surface states are all Dirac fermions of one kind or another. Only here, the velocity of the Dirac fermions is not going to be speed of light. I'll come back to the velocity later. So it's a kind of emergent Dirac fermions. Although, of course, the electrons are ultimately Dirac fermions in the high energy scale. They become non-relativistic at low energies, and then they become relativistic again in the lowest energies in these materials. And so here's how we can actually build an Unread DeWitt detector, perhaps. what we can do is we can place that quantum dot right here on the edge of the system. And what I do is I turned on a magnetic field, and the color here is going to give the spin of the electron. So the fact that I'm plotting color shows that there is a spin qubit sitting here. And in the simulations, unfortunately, I did not treat the spin qubit as a quantum effect, a quantum qubit, but actually just basically it's just a static magnetic moment, because then that at least I was at least it's efficient for the simulations. We hope to generalize to having a quantum qubits in the future sometime. So then what I can do is I can place an electric field over this region by putting down so-called top gate on the top. Where the top gate here is just a piece of metal you put on top of the system, and you apply a voltage to that metal, and it produces a magnetic electric field through that region. And Dirac fermions, though, it basically produces a potential barrier in this medium. And Dirac fermions would like to penetrate such barriers. But here I'm going to crank it up to 15 volts, and I sort of get out of this relativistic regime back to a non-relativistic regime, so higher energies. And I can just so what happens is it just pushes the electrons around away from the edge. So now these electrons are flowing around the system, but now they see that they think the boundary of the system is this region here. And so I can use this play of the electrons to go back and forth between the having the gate present and not having the gate present. So, for example, so we have we encode quantum information on the qubit, and then we can flash the coupling like that, and send it out into the field. That's the kind of basic idea, and then we can gain control over our under a DeWitt detector in a very detailed way. And ideally, what we would like to have is a very short time. If we have a very short time for this pulse, then this complex time evolution operator would become something simpler, just a more straightforward unitary operator. And that makes it easier for us to makes it easier to analyze the behavior of the system and figure out what should happen. And how do we know how short this time is? Our argument is really we want the time to be short on the scale of how, while we're turning on and off the qubit, the quantum information shouldn't spread very far from that qubit region. So so if we put in some numbers, that distance there was about 100 nanometers. Then we can actually extract by studying the spectrum from the simulation. We can extract what the velocity is, and it turns out it's 0.5 times 10 to the 6 meters per second. So below the speed of light, but which on the scale of what we're talking about here, which is really millimeters per nanosecond or nanometers. Well, anyways, millimeters per nanosecond. It's or micrometers per nanosecond. It's 0.54 millimeters per nanosecond. And that converts to, we want to turn the gate on and off on a scale of 200 femtoseconds, which is extremely fast. Faster than any modern electronics can actually control. So we started, this is my next, I guess that's sort of the conclusion of this mercury telluride platform. So we started branching out, and we looked at graphene and the literature more, and we found there's actually a fairly long history in condensed matter physics of trying to get quantum information to propagate from a qubit to another qubit through a field. I mean, it's not a very big subject that maybe it's not viewed as a particularly promising avenue, but nevertheless, it has been studied. And in 2007, there was an influential paper on graphene nanoribbons. Now, graphene is a two-dimensional carbon honeycomb lattice, and it is famous for being a condensed matter Dirac fermion system, famous enough to win the Nobel Prize, kind of famous. And carbon can come in all kinds of different forms. And in this paper, they wrapped the sheet into a nanotube or nanoribbon and created the following setting where you put a qubit on one side and a qubit on the other side. And you could get actually that these two qubits could talk to each other through the Dirac fermions propagating in the middle. So that's 2007. For this system, the speed of the Dirac fermions is well known and maybe double what we had in the previous one. So it requires even a shorter gate. So that wasn't necessarily very helpful. We turned to other systems, and let me tell you about the one that turned out to be the most promising. These are this modern Moiré pattern materials. I don't know if you've heard about these. There's been all the rage in strongly correlated electron systems and condensed matter physics. All we do is we have it's not graphene, but it's sort of like graphene. It's a transition metal diachel cogenide, TMD material, which is a honeycomb lattice with where the atoms are two different types of atoms. Like there's one layer here. It's kind of hard to see in this picture, but like one layer is red and blue, and the other one is green and orange. And when you have these two different atoms, then the Dirac fermions gain a mass. So it's massive Dirac fermions instead of massless Dirac fermions in the case of graphene. And what you can do is you can put two of these on top of each other. And because if you choose two different materials, here we had tungsten selenide and molybdenum telluride. Two different materials have two different lattice constants. And so by just placing two materials on top of each other, you get you get this huge Moiré pattern. And that Moiré pattern introduces a very long length scale in the problem. And that length scale changes all the time scales and everything that are necessary. And you end up with, we could get a switching time of 2 picoseconds, which is now getting into the realm of what electronics are possible, what's possible with electronics. So I have other platforms I could tell you about, but let me mention now what we're actually doing at Binghamton, and this is happening actually as we speak and into next semester. Largely, this effort is led by Eric Aspling. It's again in collaboration with John Marone, but we have several more team members at Binghamton, including Anna Laura Elias, who is the grower who can grow these TMD materials, and Mengen Wen, who can study defects in these materials, and Zhong Lin can study things optically and is a 2D material experimentalist. And what we're going to do is Anna's going to grow monolayers of tungsten sulfur, tungsten selenide. Actually, I don't know. There's several different options. I think it's tungsten sulfur. This paper I took this image from is tungsten sulfur 2. So it's one of these TMD materials. And just sprinkle it with vanadium defects. So we can control this at some level, the average separation between defects. So if we have a 0.4%, then you get a fairly large distance away between qubits. We actually claim now this is some of Mengen's work that these vanadium atoms are actually going to be qubits. We can use them to be qubits, and then we can control and look at different settings for different densities of qubits, these are not going to be nearly as impressive as Maxime's talk that had happened earlier, where he got very far with experimental realizations of under DeWitt detectors. But at the same time, it's a totally different platform. So, so we're hoping for that we could take it from this stage and go to this stage where we have a Moiré system down the road. And these Moiré systems are known to be able to host these topological materials, that kind of thing. So pull the story fully together. And so what we're going to get in the end is an experiment with unread DeWitt detectors. And as far as I understand the state of theory of these things, that we really have only been studying a lot of models, and we're going to be faced with some experimental data. And that might have all kinds of complications that are real world complications. So we're maybe in great need of experts on modeling UDW detectors that could help us better understand what might happen in these experiments. And I guess lastly, I could just end with a comment, or am I out of time? Okay, right. Yeah, I just wanted to mention at the end that everything is relative, and in our system, the qubits are stationary in the Dirac fermions that are finite temperature T. And I wonder, if everything's relative, can we learn from the opposite case where the Dirac fermions are 0 temperature, but the qubits accelerate? So can that problem that is sort of extensively studied here in the RQI circuit, can we take information from that and help us figure out how to make these qubits nice qubits that don't talk to their environment? The central problem in quantum information sciences, qubits are always losing information to their environment. So yeah, I guess with that, let me end my talk. I could just throw my summary slide where we simulations, and yeah, I'll leave it at that. And I'm happy to take any questions.
Amazing. Thank you so much, Michael. All right. I do have a short comment, which is that so in the IQC in Waterloo, people are trying to use superconducting qubits in order to mimic the effect of the interaction of particle detectors with, in this case, with the electromagnetic field itself, but in waveguides, basically, right? So and then we have like dedicated students who are trying to connect the physics of what actually goes on when you try to use this switchable superconducting qubits in order to couple for finite time with the field and things like this. And then we find that there are many different things, basically, right? So that happen between the standard switching with the constant gap and everything, particle detector model, when you actually go to these physical systems. So in this case, using the edge modes and the alternative approaches that you want to use here, if I were to ask you, what would be one or two concepts from the standard UDW detector that will change if you were to try to adapt them more realistically for these physical systems? What would you say that these would be?
So can you be a little more precise? So you're asking, it's a standard model of a UDW detector. How would I change it in order to apply to this setting? Is that what you're asking?
Basically, yes. Basically, the idea is is there any simple concept that I could go and change in the UDW model in order to get the theoretical model to be closer to these physical systems?
Yeah. So in the next talk, we're going to answer pretty much that question. So Eric is going to talk about our model and theoretical aspects of this. So you'll be able to, so yeah, I guess you might even think that this is a two-part discussion, although I'm not sure we didn't initially plan it that way, but we decided near the end it would be good if I just didn't focus on the theory part and let him have a go at it. So but as far as I can tell, what we can do here with the Dirac fermions is we can bosonize them. So you'll see this in the next talk. And then you just get a boson coupled to a qubit, and we can just lift things out of the literature on that problem. So that's roughly what we've been doing. But anyways, I don't know if I want to steal Eric's thunder.
Yeah, I think let's let Eric answer that then. So let's thank Michael again. So, thanks for the talk, Michael. That was very interesting. Eric, are you okay? Amazing.
Hello.
Yeah, we can hear you. That's great.
Great. Very good.
So you got
All
a question
right.
even before you started your talk. Do you want to start screen sharing?
I do here. Let's see. How's that look?
Yeah, that's good. It's not full screen. Is that how you want
I
it
will
to
make
go?
it full screen, yeah. Give me just a moment. All right. Yeah, I was really hoping that Michael wouldn't steal my thunder there because I was excited about this talk. We have been utilizing a lot of the work out of Barrio RQI. And I'm really excited to demonstrate what we've been doing with it and how we've been using it to connect these condensed matter systems, especially in the way that that you guys might be familiar with these UDW detectors. So in essence, I wanted to show you that, and the way I wanted to show you that is that these condensed matter systems can be thought of in the realm of conformal field theories. So these applications that I'm going to be demonstrating and that Michael showed you the experimental form of them, we realize the UDW detector model through these conformal field theories. So again, just a quick motivation. I'll show you this cartoon slide that basically demonstrates some of the systems that Michael showed, where we had the bulk system. You can imagine that the bulk system had the where he showed the bulk system, and then these left and right moving edge states were the very white borders, and then we had these cadmium telluride Q dots that were placed around the outside. And we can turn on and off the interaction by lowering the potential well that was created with that top gate that Michael said. And this demonstrates also the scalability of this program, where we can scale up the system by just adding more of these systems on top of each other. And and one feature of this was the all-to-all connectivity. And we can demonstrate how this all-to-all connectivity can be scaled up in some very, again, most of my talk will be idealized up until the very end, when we start to recognize, as Rick said, where some of the real world issues start to come into play. But the idealized system, where we open up the potential well on two sides and create a bulk between the systems, such that these topological edge states only exist on the boundary, but they do so between both the systems. And now if you see that if we take detectors like C and B, there's a direct communication in figure D there, as opposed to in figure C, where the C and B are in order to communicate, they'd have to utilize A as an intermediary. But this is sort of like the cartoon model of what Michael was telling about with this topological edge states and the cadmium telluride quantum dots. So in essence, we want to recognize the UDW quantum computer Hamiltonian. So we've been calling this, affectionately, the Unruh-DeWitt quantum computer. And in essence, the reason being is we wanted to, in order to realize this connection, we wanted to realize these spin qubits connected with quantum fields. And it turns out that that's kind of a common thing in condensed matter literature, and it's known as the Kondo impurities. So probably many of you are familiar with the Kondo impurities. And we can write down some sort of interaction Hamiltonian that links the Kondo impurities as a spin qubit. And that's just connected through some coupling J to some Dirac fermion current, right? With left and right movers given by the pluses and minuses, right? These Kondo qubits can then, they take the nice form that when you apply some sort of like external magnetic field to the system, that it really shows up as a two-level spin structure system, where we have a true, Unruh-DeWitt detector with two levels, different energy scales with a coupling. And we'll talk a little bit at the end about some, realities with this coupling. But for now, let's stick with the idealized model. And there's some issues with this literature. I mean, Barry RQI, you guys are you are fully aware of a lot of issues that are going on here. Fermions are hard, right? And there's been some perturbative treatments with fermions, but in general, we're not interested in perturbative treatments. We're interested in strong coupling. That's going to be a very key takeaway from this, is the strong coupling. And fermions are just really complicated. But we have a little bit of promise. We have lots of room to work with. If you look at equation 5, we have the full fermionic Luttinger liquid Hamiltonian. And in this, there's several blocks of different physical systems that we can utilize. And as I'll show you, some of these blocks of this Hamiltonian, especially this J3 block, will really come into play and really do a lot of work for us here. But this full Luttinger liquid Hamiltonian is very common in the literature. Like I said, a lot of this stuff is very well understood. But in order to do it, we really want to bring it in the UDW model that you guys have been working on so hard and have done a lot of good work with in the past decade and a half or 2 decades or so. And so those of you who aren't familiar, we just have this Unruh-DeWitt detector. It's a 2-state system coupled to a quantum field. And the coupling is really, it fully relies on the switching function and the smearing function. And this is what allows this spin moment and scalar field to couple together through some coupling constant that I've labeled J, which is not the traditional lambda for the community, but it is in the condensed matter system. So And then we have a goal, and here's the goal, and that is if we have two detectors like these cadmium telluride Q dots, and we want them to communicate through this field, then we're going to have to set up a system like this. We're going to want to utilize quantum Shannon theory because this is the theory of quantum communication, and these qubits are gonna communicate through the quantum field, and we're going to effectively measure the coherent information currently. If there's time, I'll talk a little bit about how we're going to extend that into something a little bit more rigorous than coherent information. But in essence, we can measure the coherent information, and then I get to your guys' work at Barrier RQI and all the excellent work you guys have been doing. So here we have this is the work that's done by Pitar, Aida, Akim, and Eduardo. And what they showed was that if you have a unitary gate that looks like this with one of these field operators, it looks like a controlled unitary, right? And you can set up this structure so that it really models this interaction here, or these unitary couplings here. And this unitary is, it's pretty easy to set up. You can just set it up with a single scalar field and a single UDW model. But unfortunately, this single controlled unitary results in a loss of quantum information because in essence, you're really like spreading the entanglement out between the fields and the qubits. So this isn't going to work. But what Pitar and everybody found out was that you can actually introduce a second controlled unitary gate. And this second unitary gate has some very strict restraints put on it. But when you show those restraints, you get to write down this nice quantum channel here. So I really want to point out, and this is going to be one of the really important parts of this talk, is that these field observables, these 8 vertex operator looking like field observables show up in this correlation function in the quantum channel because the field is traced out. And that's an important fact because these have really natural extensions in conformal field theories, right? Like these are just 8 vertex operators that are we're worried about the correlation function of 8 vertex operators, which shows up a lot in different conformal field theories. So, ultimately, well, let's not get into the other aspects of that, but regardless, we have, if we want to pay attention to the field's role in this field mediated communication, it really exists at the level of this correlator. Okay. So, what we want to do, so we're going to choose a Gaussian smearing function. And what we really want to do is measure the coherent information. If we have a quantum channel that looks like, equation 11, and with the correct constraints in place, and to see all these constraints, you can look at either Pitar's paper from 2019 or 2020, and my paper from that we put out in September. Both of those will be in the end of the talk. Those are where we go into very rigorous details about all of the constraints that you put on the model. And when you do, Pitar found this really nice, in one dimension, this really nice plot where he plotted coherent information to channel capacity. And as you can see, as the coupling strength over the smearing function, that fraction gets larger, the channel capacity, which is a measure of communications between the qubits, reaches the prime objective of 1, where it becomes perfect communication. So this was really exciting for me to read. I really think this paper by Pitar and L will be a really big it'll be really big one day when people start to realize the importance of these models for quantum transduction, for quantum communication. I think that this work is going to be really important. So let's revisit our fermion model. What can we do with this work, right? This work is not, this work has been around. What can we do with it? And it turns out that we can take our Hamiltonian with the Kondo impurity and the Luttinger liquid. We'll still look at that electron block, or the electron current block of the Hamiltonian. We'll set it up and we get a unitary. If we set it up with the UDW model, we get a unitary that looks like this, where we have in equation 14, where our observable O is some fermionic observable, but it's a quadratic coupling. Quadratic couplings are hard. You need a quadratic coupling with fermions because you need to preserve the number density, or the fermionic density. And so we just have this model that's just difficult to work with because it's fermions, but we really quick. Conformal field theories in general, they're going to play a big role. There's lots of conformal field theories that have equivalent in condensed matter systems. If not the system itself, then different analogies like the Kutayev-Honeycomb model, Ising model, the SYK model. All of these utilize conformal field theories. So this measure of field observable correlators is really going to be determined. The usefulness of this field observable correlators is going to be determined by how well we understand those correlators in these CFTs. Ours, we're doing the Luttinger liquid, and the conformal symmetry provides a straightforward mapping between the fermions and scalar bosons, and this is where things become really fun. So if you're unfamiliar with bosonization, it's just a straight mapping of fermions to bosons. And the thing that's interesting about this model, about this mapping, is that at the level of the correlators, there's an equivalence. The equivalence is that at the level of the correlators, the fermions are identical to the scalar bosons, which is exciting because that means we can take our difficult fermion model, we can bosonize it. I got to go a little bit faster because I don't want to go too much over time. And what we can show is that if we want to recover the same channel capacity that Pitar et al. Were able to find, then we want to take we want to bosonize our system. Oh, I do have to show you one other thing. If we look at equation 23 here, we have our original gate model with our two fermionic operators, and we bosonize it, and now we're down to a single scalar field, which, if you recall, did not preserve entanglement. If you wanted to use it as like a quantum state transfer channel, it did not use that field to transfer the entanglement. Instead, what it ended up doing was spreading the entanglement out. But if we look at that full J3 term of the Hamiltonian, we have both the current density and the current, the electron density and the electron current, this rho and J here, right? We plug them into our model. Now, this is a bit of a toy model and a bit of an idealization, sure. But we plug them into our model, and what do we find? We find equation 26, which has the exact same structure that Pitar was able to produce with his scalar fields. And subsequently, we were able to produce the same type of graph that showed that this channel that was produced, again, let me remind you, produced by quantum dots coupled to these fermionic fields, okay? Through this helical Luttinger liquid, these topological edge states, we were able to produce the exact same gates that Pitar showed at the limit of infinite coupling, resulted in perfect channel capacity. There's a lot more to this full Luttinger liquid model, right? Each one of these bosonization processes has a different system that you could look at. Each block of the Hamiltonian is a different physical system. Each bosonized form or fermionic form provides a different channel that would be interesting and have different quantum information properties. These are not easy. These cosines and these sines have been absolutely destroying me as far as trying to find these quantum information calculations. But these are things that we have to consider. I mean, look at the interaction type. The third one down, we have backscattering. Backscattering is a real issue in these systems physically. And to understand the bosonic form and the channel that would show up from the type of operators that come from this is something that really does need to be evaluated at some level. But what can we do with this? I mean, there's not just experimental progress in this. We can actually talk about theoretical progress in quantum Shannon theory applications, right? One thing that we did, and we put the paper out in September, is that we actually showed that instead of wrapping all of that switching and smearing function in the coupling constant, if instead you model it as just another parameter, what does it look like? And it turns out that it looks just like a dephasing parameter, because really the goal is if you wanted these coherent states to be orthogonal. Okay, and that's one of the restrictions we talk about a lot is these orthogonal coherent states, because coherent states are famously non-orthogonal, right? So these restrictions in place force that orthogonality. Then, if you wrap up all of that switching and smearing functions into a parameter, it looks a lot like a dephasing parameter that kills the off diagonals in the mixed out density matrix that is the coherent state density matrix, right? And so here in equation 32 and 33 is really the recognition that we're taking the coupling constant and the smearing of the field, and we're recasting it as some dephasing like parameter, okay? And what do we get? Well, we can actually add extra detectors that make noise to the system. We can use this letter B as a ratio of the coupling to our wanted detectors versus unwanted detectors. And what we can find is we can actually model this noise really simply without having to add a significant amount of vertex operators to this correlation function. Because of course, nobody wants to do that integral. Nobody wants to integrate over 12, 16 vertex operators. So instead, having a dephasing like parameter and then modeling this like it's a bosonic dephasing channel, which of course it's not, but it looks like one. In the most traditional sense of bosonic dephasing, which is just destroying these off diagonals. We can actually model this noise with these detectors as, with coherent information very straightforwardly. And we see that in some cases, if the coupling to some detectors, we notice that you can actually increase the coherent information for a short period of time at these different energy scales. But nevertheless, it's just, I think the takeaway was that, different viewpoints give us different models or different, it can make the calculations a little bit more feasible, right? So I'm running out of time. I guess my conclusions are, where are we at? And here comes the reality of the problem, right? The theory, we have a UDW model with Kondo and Luttinger liquids. These are all well established. The experiments, well-known TMDs and quantum Hall effects, as Michael showed you. But, we're not interested in this, and we're not interested in this. We're interested in this, right? Quantum transduction and quantum materials. That's the goal. And with it comes a lot of issues. You have the Kondo problem, the RG flow. You have the Hilbert space dimensions because there's no such thing as infinite coupling strength. You have self-interacting and backscattering parts. You have bulk interactions, time evolution. I mean, the list goes on and on of these things that are going to be real considerations that we have to look at. So to do that, we need a lot of time. We need a lot of collaborators, people who have done with this stuff. But ultimately, the goal in this is that the quantum transduction gives us a first look at fermionic flying qubits, right? That's an exciting aspect of this, right? Those Dirac fermions in the topological edge states are actually carrying the quantum information. So we have a first look at fermionic flying qubits. Another thing is these thermalization in quantum materials is a topic that people are very interested in the condensed matter community. And these things, they might not be industry standard, but some of these have direct analogies to what Rick was talking about with superconducting qubits and transduction. That's a very important concept right now in industry. And I think that models like this, that we can actually realize this transduction in electronic systems and fermionic systems, might actually shed some light on those more industrialized systems as well. So with that, I thank you. And here are some references if you're interested in looking on more.
Amazing. Thank you so much, Eric. Thanks a lot for this talk. This was truly interesting. Are there any questions here from our Zoom audience? Like, if not, I do have at least one question, which is that how relativistic can you go? Like, up to which extent, like, can you play with like an analogous to the speed of light, or talking about causal separation or something like this, up to some extent at least?
I mean, the theory itself is relativistic in nature. I have like a lot of canned answers for this, but I feel like someone who understands as much as you do and your group does, I feel like I won't give a satisfying answer. The reality is that in these topological systems, we sort of treat the Fermi velocity like it's the speed of light, like that's the Lieb-Robinson bound or whatnot. So that's not going to be. So whether or not relativistic effects come into play, we don't know. But they're calculable. I mean, this stuff is. It's like I said, it's relativistic in nature. So if there's relativistic effects to be concerned about, they'll show up, and we'll be able to account for them. But in the sense of what we're doing, we really are just sticking with, Minkowski space-time. Things are really flat here. So we're not worried about like a lot of the relativistic effects that, the general RQI community is worried about. And, but it is a relativistic theory in nature, so it would be interested. We're interested in exploring that system, sure, or exploring that regime.
I could add one point to that question. So the reason it's Dirac fermions is because when you have a Fermi surface in non-relativistic setting, when you linearize near the Fermi surface, you get a linear velocity. So you lose the relativity when you get to higher energies. So it's an energy statement. As long as you're working with energies below a certain energy cutoff, then it'll be pretty much perfectly relativistic.
I see.
So I don't
No,
know
yeah,
if
this
that's
is
what
pretty.
you're looking for.
Because we have a lot of protocols, I don't know, like entanglement harvesting, things like this, which rely on well, you talking about causal separation or about some sort of speed limit and things like this. So it's just wondering up to which extent you guys can implement it there. But it's very nice that we have this analogy between this, and thank you so much for coming here and presenting this work. This is truly interesting stuff.
Thank you.
Amazing. So let's thank Eric again. And we head to our next speaker, Daine. All right, Daine, can you say a couple of words for us?
Yeah, of course. Can you hear me?
Yes, yeah, amazing. We can hear you for sure. So while you set up and
Good.
you start screen sharing, let me just give some announcements. If you are watching us on YouTube right now, you might have noticed that the schedule has kind of like changed, and it changed because we had a last minute cancellation, so I had to kind of move quickly and talk to the speakers behind the scenes and make sure that everything would work. So we do have a new schedule. It should be updated in the YouTube description if you're watching it on YouTube. And so yeah, that's about it. So now it's Daine. The next speaker after Daine will be Benito, and from that point on, we keep going as normal. So Daine, are you going to do a Blackboard presentation, or are you going to?
No,
Okay.
no, I have some slides here.
Amazing. So our next speaker.
So hopefully you can see these.
Yes, we can see everything. It's not full screen yet. Like we can still see the slides in the corner.
I see what's going on here. Just a minute. Sorry. Here we go.
Amazing. So our next speaker is Danielson. So Daine is going to talk about horizons as eavesdroppers. So please, Daine, the floor is.
Yeah, well, thanks. Thanks, Rick, for the introduction, and thanks for helping organize this very informative RQI circuit. So I'm going to be talking about some recent work done with Gautam Sadashandran and Bob Wald, and also some more recent follow-up work to appear soon with Jonah Kudler-Flam. And most of what you'll see today, can be found in these various papers listed at the bottom of the screen. And the punchline, as you can see from the title, is just to understand that horizons as instruments or generators of quantum decoherence, or horizons as eavesdroppers. So I'm going to begin with a thought experiment, which will help to motivate why you should believe that horizons are eavesdroppers before we do an explicit calculation and show them to be such. So imagine that I had a spatial superposition of a massive or charged body. It was created, let's say Alice is the experimenter with the superposition, and she created this superposition far in the past. So that's coming in on this space-time diagram from off the screen in the far past. She's used a Stern-Gerlach apparatus to put this particle in superposition. And as she enters this causal diamond that I've outlined with dashed lines, Alice is going to attempt to recombine the left and right branches of her superposition, so that by the end of the causal diamond, she's going to perform some kind of interference experiment and look and see whether her superposition has remained coherent or not, which I've depicted with this cartoon of either a particle-like Gaussian or a kind of more wave-like interference pattern. more concretely, Alice could implement such an experiment by, if her spin was a superposition in the z direction, she could measure the spin along the x-axis, and assuming she controlled the phases of her superposition sufficiently well, she would know that the state of her system after the spatial superposition was recombined would just be an equal superposition of spin up and spin down in the z direction with uniform phases, which of course is a definite spin up in the x direction. So if she even one time measured in the x direction something other than spin up, she would know in one shot in that instance whether or not her particle had remained coherent. So this is a practical way she could, in principle, determine her coherence. Okay, so Alice's particle, of course, is entangled with its own Newtonian field. Formally, you can describe this as kind of tensoring in some coherent states of the field psi1 and psi2 of the linearized graviton field, say, with Alice's particle. And so imagine now you've got this Newtonian field attached to Alice's particle, and in a space-like separated region from Alice's recombination, there's an experimenter, Bob, who's going to attempt to measure Alice's superposed gravitational field just by releasing a particle from a trap and allowing the particle to evolve, and it'll evolve into a superposition of trajectories depending on which Newtonian field it's in. And so that'll tell him which Newtonian field his particles become entangled with, and therefore he can learn which path information about Alice. Okay, Bob, of course, doesn't have to release his particle from a trap. He could keep it in the trap if he wants. He has this free choice of doing a measurement or not. If Bob successfully measures the field, then Alice's particle has to be decohered in the which path basis. But Alice can tell whether her particle is decohered at the end of her experiment by this interference problem this interference protocol that she follows. And this seems paradoxical because, of course, Bob is doing everything at a space-like separation from Alice's process. So it would seem as if Bob could affect the decoherence of Alice's particle by choosing to release or not release his particle, choosing to become entangled or not entangled with the field sourced by which path Alice is on. Okay, so obviously there are no, the paradox is resolved. This paradox is resolved in an interesting way, though. So in quantum gravity, linearized quantum gravity, and also in QED, where you can pose the equivalent paradox with charged particles, the vacuum fluctuations of the metric or of the electromagnetic field are vital to resolving this apparent conflict between complementarity and causality. So really, Bob has to resolve the position of his particle better than some uncertainty, little delta x. But that has to be bigger. That separation of his particle, little delta x, has to be bigger than the intrinsic uncertainty on the position of the particle due to vacuum fluctuations. So even if he controls the wave function of his particle, its center of mass degree of freedom kind of could be localized as well as possible from the point of view of quantum mechanical dispersion, there's an unavoidable amount of uncertainty that places a bound on the precision of his measurement just due to the fact that it couples to a quantum field and that introduces vacuum fluctuations. So that means that Bob can't perform the measurement even in principle over an arbitrarily short amount of time. There's a fundamental limit on how long it takes for him to resolve which path his particle is going into. That's dictated just by the quantum field he's coupling to itself. And meanwhile, Alice needs to avoid decohering herself. Of course, if Alice does a bad job of her experiment, then she could radiate gravitons or photons off to scry, and she would decohere herself. So she needs to do the experiment adiabatically to avoid as much radiation as possible. But this ends up having the effect, well, you can quantify this. You want to make sure she emits a number of entangling photons, the expected number of entangling photons that's much less than 1. If Alice goes slow, then she can minimize this number of entangling photons, just because she can have less and less radiated power. But Bob has to measure from farther away because, of course, the protocol is that Bob has to be outside the causal diamond of this recombination process, which is when Alice is moving her particle. So the slower Alice goes to avoid decohering herself, the further away Bob is. The further away Bob is, the weaker the Coulomb field or Newtonian field is that he's trying to measure. And so the longer he has to wait before the relative displacements of the two superposed paths of his particle will overtake the uncertainty due to vacuum fluctuations. And it turns out all of these things exactly perfectly balance, as we showed rigorously in a paper in 2022, so that there's no causal paradox. Okay, that's great. But what if everything we've done so far is in flat spacetime? What if we run the same analysis in a black hole spacetime? So what if Bob is behind a horizon? Well, now something has changed. I just told you that Alice has to perform her experiment as slowly as she can, or she would like to perform her experiment as slowly as possible. But this is going to force Bob to make measurements at farther and farther distances, which are more and more difficult for him to make. But that statement is not true if there's a black hole in the spacetime. In the exterior of a black hole, Alice can take an arbitrarily long amount of time. She can do her experiment as adiabatically as she likes, as slowly as she wants. And Bob could, nevertheless, as is kind of evident from this Penrose diagram, Bob could be just behind the event horizon of this black hole, even if Alice takes an unboundedly long time to do her experiment. So Bob is no longer forced to be far away. He could be just right over there behind an event horizon. So this sounds like a problem because now, I'll make the black hole big. There's no fundamental limit on Bob's ability to resolve which path Alice's particle has taken. And there's no fundamental limit because he can, make the black hole big enough that he can integrate up for however much time he wants. And Alice can take as long as a time she wants because, and Bob is not forced to go any further away from Alice. Okay, so this seems like a paradox again. And we were puzzled by this, but we noticed there would be no paradox if one thing were true. There would be no paradox if Alice was decohering at a constant rate, as if she were becoming entangled with any number of optimally sensitive experiments hidden behind the black hole horizon. So if the black hole decoheres Alice no matter what, just due to the existence of the black hole, then there would be no paradox because Alice can't possibly learn about the presence of Bob, because Bob might be there or not, but Alice will decohere the same way. And this is, in fact, true, and this is what I'll show in the rest of the talk. So, okay, suppose Alice is now doing the same experiments before, but she's in a stationary laboratory outside a black hole. Now, why would this be different from flat space-time? And I gave you this kind of paradox reason, but more concretely, what's the difference? So let's warm up with displacing a classical electromagnetic charge outside a black hole horizon. I'm going to use the electromagnetic case for the explicit calculations, just because less indices, it's a simpler calculation. So if Maxwell's equations on the horizon take this very nice form. It says that the time on the horizon, this V, big V, is affine time measured along the horizon. The time derivative of the Coulomb field sourced by Alice's particle will be equal to minus the angular divergence on the spherical cross sections of the horizon of the electric field. But if you think conceptually about what this is, these capital A indices are angular indices. So this divergence on the horizon is radiation. It's modes that are tangent to the horizon or transverse to the propagation direction of any, they're kind of transverse modes as far as any photon falling into the black hole is concerned. And so what this equation is saying is that a time change of the radial component, the Coulomb field of the electric field, inevitably gives rise to radiation modes that then will propagate into the black hole interior. Now, Alice is doing everything very slowly, so her potential is changing very slowly. That means that the electric field sourced on the horizon can be very small. But nevertheless, because there's a net change in the position of her particle, there has to be a net change in the Coulomb field registered on the horizon. So that means that even though at any given moment in time, E sub A, the kind of electric field, the tangent electric field on the horizon might be very small at any given time, I can't approximate it by 0 because it has to integrate up to a finite number in order to give rise to a net change in the Coulomb field. But that means that since E sub A is the time derivative of A sub A, there has to be a net change in the angular components of the 4 potential that cannot be neglected for a consistent description of the problem. So in pictures, there has to be a net displacement between early and late times of the 4 potential on the horizon. And of course, the 4 potential is gauge dependent, but changes in the 4 potential are gauge invariant. And this will look familiar to anyone who studied the electromagnetic or gravitational memory effects. This is a mathematical analog, exact mathematical analog, but on a black hole horizon. And unlike the memory effect at null infinity, this occurs in all number of space-time dimensions. So this displacement of the 4 potential gives rise to a low frequency behavior that diverges in the Fourier transform that diverges at low frequencies. Basically, you have some step function like behavior, you're going to get a 1 over omega piece in the Fourier transform of the 4 potential. But if you compute the number of photons produced due to such a 4 potential through the horizon, the form of the number, the form of the Klein-Gordon norm, which computes the number of photons, dictates that any such 4 potential that undergoes this displacement diverges. So there's an infinite number of these photons, even though they're very low frequency, arbitrarily low frequency, there's an infinite number of them. This is going to give rise to an infrared divergence. Now, of course, in the real experiment, Alice displaces, creates a superposition, and then brings it back together. So there'll be some finite time interval, delta V. But still, there's going to be some growing number of soft photons that are produced. And this number of soft photons is going to grow like, delta, there's going to grow like n down here, expected value of n. There's going to be a logarithmically growing number of soft photons lost behind the horizon. And this is just due to the fact that she moved the particle at all. So it's an unavoidable effect. And more than that, as a function of Alice's proper time, the difference between the branches of her experiment sources a number of photons that's growing linearly in her proper time. I said it was growing logarithmically, but that was in terms of time on the horizon. There's the surface gravity and an exponential factor convert the logarithmically growing affine time on the horizon into linear growth of time here. So, okay, very good. So if I plug in numbers, we find that Alice's decoherence grows like the following rate. And if our sun were a black hole, an electron on Earth superposed by a meter would decohere in 10 to the 32 times the age of the universe. So I would not say this is an effect we should worry about. But if the experiment were done close to the black hole innermost stable orbit, it would decohere in about 5 minutes. So, that's still probably smaller than the effect due to the whatever accretion disk might be near an astrophysical black hole, but the effect can be large if you're close to the black hole. And of course, there's an analog in linearized quantum gravity, which is even weaker, but maybe more interesting because all objects source gravity and gravitational fields can't be shielded. So there's no way to avoid sourcing superposed Newtonian fields inside the black hole. And so there's a universal decoherence, at least due to quantum gravitational effects. And for the last section of the talk, I'll just mention this upcoming work, which is that so far, from Alice's perspective, you can recast all of this in the language of quantum information theory and exact or approximate quantum error correction. So imagine that you can understand the effect of the black hole as some quantum channel acting on Alice's superposition, and you can compute the fidelity between her initial and final states, given that she's been decohered by this quantum channel, and even give her an optimal recovery channel D. And this fidelity is going to describe her decoherence. So for clarity's sake, in the discussion, I'm going to use the Holevo fidelity, which is just some technical detail. It makes the calculations easier, and you can show that it's a very good approximation to the kind of more standard Ullmann fidelity. But okay, that's some nice mathematical formalism. But I'm going to now tell you this is related to the story I told you at the beginning about Bobs hiding in the interior of the black hole. Because, yeah, so, okay, then this is my last slide, so I'll just say that. The punchline is the trace distance, it gives a measure on the distinguishability of states on the interior, but for an optimal possible measurement. And for Bob in the black hole, for any imaginable Bob, this bounds his ability to resolve states on the interior. But the trace distance is tightly bounded by this fidelity. And so what we show is that as a function of time, as the fidelity, as Alice's particle decoheres, the ability of any optimal measurement on the interior grows in such a way that they're actually equivalent. So the decoherence of Alice is equivalent to the probability of an optimal measurement on the interior of the black hole to resolve the difference between the field states that are set up by Alice's experiment. So decoherence due to the black hole is equivalent to the decoherence due to optimal measurements performable in the black hole interior. So that's basically it. And I probably don't have any time for questions, but thank you very much.
Thank you, then. Yes, unfortunately, you ran a little bit out of time. But if there are other questions, I'm sure that people can reach out to you, either via email or they can even ask it here in the chat. All right, Daine, thanks a lot for your talk. Now
thank you.
We head to the next speaker. So the next speaker is going to be Benito Juárez-Aubry.
Hey.
Hello.
Can you hear me? Can you see me?
Yes, we can hear you perfectly, and we can also see you. So yeah, feel free to.
Okay, so let me share. What's that? Is it like full screen like that? Probably. Does that look okay?
It looks amazing. Yeah.
Okay, thank you. All right. So I'll start when you tell me, Rick.
Well, then let me introduce you. All right, so the next speaker is Benito Juárez-Aubry, and he will talk about quantum strong cosmic censorship and black hole evaporation. So please, Benito, the floor is yours.
Okay, thank you very much. I'm very happy to have the chance to talk to you all. I have to say I find this initiative very exciting, just to put that up front. I even try to maybe convince some colleagues in Mexico to have one of our own, institutional circuit and so on. But okay, unfortunately, it didn't work out. But I'm happy to be part of the last day of the miscellaneous kind of talks. Okay, maybe next year I'll try harder to convince them, right? Okay, so I want to talk about a question that has been around since, already for a good 40 plus years, which has to do with black hole evaporation. And I wanted to share my views on this issue. In particular, to give perhaps some mathematically precise, in some sense, arguments as to how we could probably think that information is not lost in a very, very particular way, which I will explain, having to do with mainly a series of arguments that seem to point, in my opinion, in the direction that quite probably at very late times in black hole evaporation, the semi-classical description of the black hole evaporation leads to divergences, which do not allow, in some sense, to say anything beyond a certain Cauchy horizon that appears on the evaporation diagram. And that, in my opinion, this indicates that the original presumption that there's a post-evaporation region where information is lost is not really justified. So I'll make the point throughout my slides, and in doing so, I'll present some kind of generic idea about strong cosmic censorship in a quantum setting. So that'll be kind of the main point of the talk, and then explain this in the context of black holes, which is in some sense the inspiration for this idea. Anyway, so let me give you my outline. Of course, everyone knows black hole evaporation, but I'll touch on the issue very quickly. Then I'll talk about the puzzle itself, the information loss puzzle, and then I'll tell you about my idea on quantum strong cosmic censorship, and then I will argue that this supports unitary evaporation of black holes. Okay. So first of all, we know that black holes radiate. In the 70s, Hawking wrote an incredible paper in which he found that black holes emit radiation. And it goes as follows. In the process of the formation of a black hole, quantum fields start getting stimulated, and there's particle creation. So this is in some sense not incredibly surprising, because black hole formation is not a stationary process. And we already knew from the work of Parker that in non-stationary situation, one has particle creations. Now, what's more interesting is that at late times, once the black hole has formed due to this stellar collapse, the creation of particles has a thermal spectrum. So in particular, in the test field limit, the radiation is thermal. So by this test field limit, I mean quantum field theory of spacetime. The radiation is thermal at the Hawking temperature, which is proportional to the surface gravity of the black hole. So for example, for Schwarzschild, we know very well that this is 1/8 pi, the mass parameter of the black hole. Okay, so this is not super surprising now after, so many years, because an exterior observer in some sense has no access to the details of whatever's going on inside the black hole. And thus a pure state, if you trace out, formally speaking, over the interior degrees of freedom of the black hole, looks thermal. Okay, so note that generically, the Hawking temperature will depend only on the mass, angular momentum, and charge of the black hole. Okay, because these are the parameters that the surface gravity is going to depend on. Okay. Now the second part of the story is that black holes evaporate. There is an energy flux at the black hole horizon that is negative. So that means that there's output of radiation is making the black hole shrink in some semi-classical sense. Now, if the black hole shrinks, it becomes hotter by this Hawking temperature formula, at least in a quasi-stationary regime. If you think this formula still is reasonable, you expect the black hole to get hotter and hotter, and eventually, people argue evaporation cannot be stopped, and I think there's good reasons to think that's the case. Okay, eventually one ends up with the following diagram, which I will explain. So this is the diagram that Hawking drew in 1975. You initially, can you see my little hand? I suppose you can. So I will assume you can, actually. So you have initially a star collapsing and forming a black hole. So the black hole region is this blue region, okay? And if you have an initial in state, for example, defined on scry minus, you have this radiation kicking in and starting to go carrying energy away from the black hole, making it shrink, until eventually the black hole completely shrinks, and you end up with a diagram that looks like that. In the far future, there is no black hole. There is a region that looks kind of flat or almost flat, and is completely full of radiation. So in this diagram, when you initially had a mix and a pure state on scry minus, you will end up with quite general arguments indicate that you will end up with a mixed state on scry plus. And of course, this indicates that this whole process is not unitary, because we don't see this non-unitary. We don't see pure going to mixed in unitary evolution. Okay, this is the information loss puzzle. How is it possible to reconcile the idea that we have non-unitary evolution in the evaporation of a black hole, and where does the information that was contained in this pure state, where did it all go? Okay. Now, it's noteworthy pointing out that the previous diagram is not globally hyperbolic. Let me just go back to the diagram to indicate why. If you start out with a Cauchy, well, not Cauchy surface, because this is not globally hyperbolic, but if you start out with what would be a Cauchy surface of some domain of dependence, you can only get up to here, for example, because at this point, there's a Cauchy horizon. Okay, so if I take, for example, scry minus, and I give initial data here, I know how to evolve a hyperbolic equation up to this point. So this boundary of this red region is a Cauchy horizon, okay? So information loss is a manifestation of this lack of global hyperbolicity. There is a breakdown of quantum and classical determinism. So breakdown of quantum determinism is what we refer to as information loss. And this point has been emphasized, for example, by people like Andrew, by people like Wald, and I think they are correct in their remark. Okay, however, there is, in the last few years, very strong evidence that Cauchy horizons are not semi-classically stable. That means that quantum effects become, apparently, under quite generic circumstances, quite important in Cauchy horizons. So the point I want to make is that this semi-classical instability is contrary to the standard information loss picture. Okay, so that this instability will not allow you to draw this diagram where there's a post-evaporation region. That's what I want to say. So let me begin by providing a precise statement, which is unfortunate that I have to talk about mathematics and so on now. Okay, so I'll talk about algebras of observables and states in curved spacetime just because the main idea is conveyed in this language, okay? So we can view algebra of observables in spacetime as associated to spacetime regions. This is kind of the moral of the algebraic approach to quantum field theory. So rather than giving you a very complicated mathematical definition, I'll give you an example, which is the Klein-Gordon field, okay? So the Klein-Gordon algebra in a fixed globally hyperbolic spacetime is a unital star algebra, which is generated by some symbols that are smeared fields. So if I give you a test function, which is smooth and of compact support, I can draw these symbols and impose a series of relations on them. So I can ask that there's a linear map from F to the smeared field. So that means that's just a distribution. I can ask for hermiticity. I can impose a field equation weakly. So that means that acting on test functions, this is 0. So you can think of it holding by integration by parts twice. And then I impose commutation relations where this is just the causal propagator. This is just the covariant version of the standard commutation relations. Now there are some additional properties of this of this algebraic construction. If you take a smaller region than the full globally hyperbolic spacetime, then the smaller region, if it's a globally hyperbolic spacetime in its own right with the induced metric, you can define an algebra in that region. And furthermore, that algebra is isomorphic to the subalgebra of the algebra defined in the larger region, restricted to that smaller piece. Okay, and then there are a few other axioms such as time slice axiom and so on. Okay, this is not, I don't want to spend too much time here. Okay, and now what I mean by states is a linear map going from the algebra to a complex number such that it's normalized. Okay, so the identity has to go to 1, and it's positive. Okay, so whenever you take the expectation value of A star A, this has to be non-negative. Okay, a state is in general defined by all endpoint functions, and then by the GNS construction, one can obtain a representation of this algebra in Hilbert space. Okay, for our purposes, all of this blah, 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 the most important one is the 2-point function. Okay, so the 2-point function has an integral kernel that everybody knows and loves, and that comes from this kind of we know very well from our master courses in quantum field theory, which is the Weidmann function. So for example, in Minkowski space, this is exactly what we know from this kind of mode expansion formula. Or there's also a closed form version in terms of Bessel functions. Okay. And a very important property of states is the Hadamard condition. Okay, so that's a condition of the 2-point function. It doesn't care about all the other endpoint functions, it cares about the 2-point function. So it prescribes in some precise way what are the distributional singularities of the 2-point function. So there is a complicated, definition, but morally speaking, think of it this way. The 2-point function is a bidistribution, so it's a distribution of 2 points. And the leading divergence in this Hadamard states goes like a smooth function, which is actually 1 in the coincidence x goes to x prime, or x prime goes to x, divided by 1/2 of the square of the geodesic distance between the points x prime and x. And this epsilon is just a regulator. It's just to give a distributional correct description of the Weidmann function. Then there's a subleading divergence, which is logarithmic, and it comes multiplied also by this smooth symmetric coefficient, okay? And then there's another piece that is completely regular. In fact, it's smooth typically, okay? So you can say this in a very precise way, but just get the right message that this goes like 1/sigma, where sigma is the squared of the geodesic distance between these 2 points. So when these 2 points are connected by null rays, of course, this is the distributional singularity. So this is exactly like in Minkowski space, but in curved spacetimes. Okay. So let me get now to this conjecture. I'll give some auxiliary definitions before I state it. So first definition. If you have a spacetime and S is a partial Cauchy surface, so a closed achronal set, such that its domain of dependence is not its causal shadow, then we say that it is a strictly partial Cauchy surface if it cannot be extended to be a Cauchy surface on the conformal completion of this spacetime, or if it admits an extension to a Cauchy surface, we say that this extension, the extension is such that if you remove this partial Cauchy surface from C, the extension, then there is an open set of C contained in the interior of the conformal completion of the spacetime. Okay, it looks complicated, but I'll give an example of why this is important. Then we have another quick definition, which is quite standard. If you have a star algebra A hat, we say it's an algebra extension of a star algebra A if A is a star subalgebra of A hat. And if we have a state on A, then we say that the state omega hat is a state extension of omega if omega hat of A is equal to omega A for all the A's in the subalgebra. Okay, so it's just a natural notion of extension. Okay, so let me get to the conjecture. Let S be a strictly partial Cauchy surface, okay, of the not necessarily global hyperbolic inextendable spacetime MG. And you take its domain of dependence to be ds. So ds with the induced metric can be seen as a globally hyperbolic spacetime in its own right. Okay, so here I'm just saying that this is the induced metric. Okay, you pull back and so on. So let A be an F local. This is just a technical condition. Quantum field theory defined over the whole spacetime, and let B be a quantum field theory free or perturbatively interacting. I should also say A is free or perturbatively interacting. Quantum field theory over the domain of dependence, okay, which is isomorphic to this subalgebra of the whole larger algebra. Then, if you have a state on the smaller algebra that is defined only on the domain of dependence, that is a pure Hadamard state, then generically, there is no extension of this state defined on the domain of dependence of this partial Cauchy surface to a state defined on the larger algebra, so in particular on the closure of this region, that is Hadamard. So what does this mean? I define a pure state in a small region that is the domain of dependence of some strictly partial Cauchy surface, and then when I try to get to the boundary of this region, so which is the Cauchy horizon, then I lose the Hadamard property. Okay, that's what it says here in words. Okay, so a breakdown of the Hadamard condition might, of course, indicate a breakdown of semiclassical gravity. For example, it might indicate that the stress energy tensor doesn't exist, but rather its expectation value. And of course, this is the source of the semiclassical Einstein equations, which are given by equation 4. Now, if the breakdown is sufficiently strong, one might develop, for example, semiclassical curvature singularities on the left-hand side. So I argue this is what happens in black hole evaporation. And so I argue final stage of black hole evaporation is beyond the semiclassical regime of quantum gravity. Now, remarks on the hypothesis. The strictly partial Cauchy hypothesis is important. And there's a good counterexample, which was mentioned to me by Jorma Loko, and since then I've understood that there are other ones as well. So consider Milne's universe, which is the future wedge in Minkowski space. It's possible to construct a pure state in that space-time that can be extended to the whole of Minkowski vacuum. But here, a Cauchy surface of Milne is not a strictly partial Cauchy surface in Minkowski. Rick, how am I doing with time? Am I still good? Sorry? Okay, so I'll speed up, but I'm almost done. So purity, of course, there are plenty of examples with mixed states that can be extended. For example, a thermal state at the Unruh temperature on the right Rindler wedge extends to Minkowski, so that's quite clear. F-locality is just a technical point, which I will not dwell into. And finally, genericity. There are finely tuned counterexamples. For example, if you take a conformal blow-up in an otherwise globally hyperbolic spacetime and remove the blow-up point, then you can define conformal states that are Hadamard everywhere in this non-global hyperbolic spacetime. Okay, a number of authors have observed the breakdown of the Hadamard property in Cauchy horizons. So, okay, for example, the Rindler state on the Rindler wedge in flat spacetime, the Unruh and Hartle-Hocking states in Reisner-Nostrom in lower dimensions than in 3+1. Likewise for Reisner-Nostrom de Sitter, and more recently with Kerr. So there are plenty of examples of these blowups. There are more importantly structural results, which I will not read in detail, like K. Ratzkowski-Wald, as you know, for compactly generated Cauchy horizons. And another result by Fuster and Ferch that talks about the blowup in diamonds or double cones or diamonds in Minkowski space, in the interior of Minkowski space. Okay, so what I think semiclassical gravity actually predicts, if this conjecture is true, is a final singularity where the Cauchy horizon would form. But now look, this diagram is completely globally hyperbolic and there's no loss of information. Of course, you might say, oh, you've traded loss of information for something horrific. Now everything becomes singular. Sure, but I think that semiclassical gravity is only as good as predicting this. Okay, there are two pieces of evidence for why I think this is correct. The final evaporation event is a curvature singularity, and if semiclassical gravity is reasonable in some sense, you would expect this singularity to propagate causally, okay, or along cones. Also, if you think that the Hocking temperature becomes hotter and hotter, then you expect a breakdown of the Hadamard condition. So this has led me to a stronger conjecture in semiclassical gravity, which I am not stating here, but it's in my preprint. And what I think quantum gravity ought to do is to resolve this final singularity and give us a diagram that looks like this, okay? So perfectly nice with a color that we don't understand at all because it's in the strong quantum gravity regime, but otherwise looking very globally hyperbolic. So thank you. I would very much like if you look at my preprint and give me some feedback. I was expecting to be the last speaker in this event, so I included this big clap for the organizers of this successful initiative. I think we can still clap even if I'm not the last one. Thank you.
Thanks, Benito. That's perfect. Apologies for
Okay.
putting it together, for managing the time and all these things. Just we had the last minute cancellation, and then I had to do something about it. And you were the perfect victim because you were the last one, right? So if I move you, then it's perfect.
Sure.
Amazing. So unfortunately, we're already running too late, and I really can't make this run later than it should. There's a Christmas party going on behind me right now at the Institute, and it's we will start hearing Czech Christmas songs very soon if we don't wrap up in time. So the next speaker is Adam, and then Helfer. So Adam, would you mind speaking a couple of words for us so that we could?
Yes. Can you hear me? Okay, good. And okay, let me know when.
Amazing. So Adam, please go ahead. The floor is.
Okay, thank you very much. Yeah, I'd like to echo the calls for clapping for the circuit. This is really wonderful. Oh no. I hope this doesn't keep happening. Yeah, and I'd like to also say how wonderful it is that the talks are available asynchronously, because I certainly would not be able to attend most of them. So today I want to talk to you about certain issues which come up when we look at quantum systems with infinitely many degrees of freedom. And I want to show you that there are circumstances in which we can plausibly contemplate the idea that infinitely many simultaneous measurements might be made. And this is something which hasn't been thought about, to my knowledge, in quantum theory very much. And I'll argue for you that the most plausible result of this, at least in the cases I'm going to look at, is that the Hilbert space can wind up being modified. And I'll be precise about what that means. Now, when I talk about infinitely many simultaneous measurements, I am not suggesting that we have a laboratory populated in any ordinary sense with infinitely many experimenters, or even one experimenter with infinitely many desires. But what I do think is very possible is that, you see, nature is probably frequently making measurements. Measurements are physical processes. I find it completely incredible that they should only be made by human actors, or only on Earth. They're happening all the time. But we do not have a theory of when measurements are made. Quantum theory tells us how to treat a measurement, given that it is being made. We apply the Born rule. But, and I think this is a really an overwhelming gap in quantum theory that prevents it from being a complete dynamical theory. We do not have any objective way of saying under what circumstances a measurement is made. Nature is presumably making that. And that's what motivates this talk. So let me start by saying what I mean by a quantum system with infinitely many degrees of freedom. This is not quite straightforward, but for the purposes of this talk, we can give a pretty good answer. So it's not just that you have an infinite dimensional Hilbert space, because even a particle, an ordinary quantum one particle on an interval, has an infinite dimensional Hilbert space, but we don't usually think of it as having infinitely many degrees of freedom. So what is the concept that I'm trying to get at here? Well, let me tie this in with how I want to look at the problem. I told you we were going to be thinking about changing Hilbert space. So I want to think of constructing any given quantum theory in two stages, where we only get to the actual construction of the Hilbert space in the second stage. The first stage is to specify the dynamical variables, like the P's and the Q's or something like that, of the canonical variables. and their abstract algebraic properties, which might be like the canonical commutation relations. So we can think of this as an algebraic system similar to the way we would specify a group by giving a multiplication table. There is not yet any representation of these operators on a Hilbert space. That is important to achieve, but that has not yet been done. The second stage is the construction of a representation of this algebra as self-adjoint operators on a Hilbert space. So basically, we think of quantum systems as described by certain quantum dynamic variables. In quantum mechanics, the P's and Q's. In quantum field theory, it would be fields, phi, and their velocities, pi. Or for, say, a spin chain, there would be the Pauli operators. And these are subject to certain algebraic rules, which might be the canonical commutation relations, they might be the spin relations, what have you. And now when we really want to describe a particular quantum system, we must not just choose this set of variables, okay, but we have to describe a Hilbert, we have to describe a representation of them on the Hilbert space. And what's going to be distinctive about systems with infinitely many degrees of freedom is that we need infinitely many of these basic variables, these basic quantum variables, to generate the algebra of observables we're interested in. So in a quantum mechanical system, we have only finitely many P's and Q's. In a finite system that spins, we have only finitely many Pauli operators. But in a field theory, we have an infinite family of phi's and pi's. And in an infinite spin system, we have an infinite family of spin operators, one set sigma x, sigma y, sigma z for every site. Okay, so let's look at some examples of this, which are familiar. And the technicalities, most of the technicalities are not important. I'll just explain in physical terms which ones are. So if we look at the, first of all, the case of finitely many degrees of freedom here, and we take the canonical commutation relation, then the Stone von Neumann theorem tells us that all irreducible representations are unitarily equivalent. So there isn't really any significant choice in which representation to construct. But in the infinite dimensional case, there's a theorem due to Schale, which says, yes, indeed, there are very many inequivalent representations. And in physical terms, this oversimplifies slightly. What distinguishes these are the infrared and ultraviolet asymptotics of the 2-point functions. So different representations of the CCR will give rise to different physics in this sense. And that's the sort of thing that's going to come in for us. So let's look at the canonical example of construction of a Fock space. So we start from the canonical commutation relations. That's the algebraic part. And then we start bringing in an additional choice, which determines which representation we construct by appealing to Poincare invariance. And we use that to split the field operators into annihilation and creation parts. And then we assume, and this is also part of the physical input, that there's a unique invariant normalized vacuum state annihilated by all the annihilation operators. And once we have that, we can construct the irreducible representation by just following our noses. Anything of the form a certain number of creation operators applied to that state is supposed to be in our Hilbert space. Okay, and we can deduce the norms of all of these states by applying the canonical commutation relations, and we can build up the entire space this way. Okay, and that's the usual construction of a Fock space. Now, I want, for reasons which are going to become clear in just a minute, also to look at an infinite spin chain. And this is not going to be the thermodynamic limit. This is going to be where you consider larger and larger finite spin change. This is going to be, we're going to assume that this is infinite from the beginning. Oh no. There we go. So in this case, we have a bunch of sites labeled by alpha, and let's say each site, there's a two-dimensional spin up, spin down. I really just care that there are two states here. And so we have Pauli operators on each side. Then by analogy with the Fock construction, we could construct a Hilbert space by assuming that there's a state which is, say, initially all down with respect to the Z operator, and allow other states which are constructed by applying finite sequences of spin operators on this. Okay. We can build that up to a Hilbert space. Okay. This follows it directly analogously to the construction of the Fock space. Okay. And these two-state systems are not just analogous to the Fock space, but we can actually regard these as being certain degrees of freedom of a quantum field theory, just some particular degrees of freedom of an underlying quantum field theory, as you'll see in just a moment. Okay, so this representation that I've described does depend very much on the generating state, which I took to be all the sites in the down condition. And other choices of generating state will be most often orthogonal to all vectors in this Hilbert space that I've constructed if the factor states are distinct, pointing different directions from the down state for infinitely many sites. So then let me bring in a very physical, simple model. Let's suppose we have infinitely many separated atoms on some time-like hypersurface. And you can think of this as being something that might very naturally occur in a cosmological model. Okay. So, and each atom will just care about two of its possible states. It could be more complicated, but we'll just care about two of its possible states. Okay, so these are really states of a particular quantum field theory, but we're simplifying. And let's suppose that for some cosmogenic reason, each of the atoms is initially in some state, which without loss of generality, we can suppose is the down state. Okay. And then we can apply the previous construction and we get a Hilbert space. But now, supposing there's an observer near each atom, and that observer measures the X component of this spin. So having done that, the atom alpha will be projected into an eigenstate of the X component, which will be a superposition of the up and down Z components. So the results of this will be coded in a set of signs, plus or minus, S is plus or minus for each alpha, okay? And the resulting state will be this product of this new set of initial states. But what I argued for you a few slides ago is that that's going to be generally orthogonal to the initial state. And in fact, it's easy to see that that's true, because if I compute the amplitude to go from the initial state, which was all downs, to this new state, okay, these guys go to 0, and I have the product of 1 over the square root of 2 infinitely many times, which will be 0. So the interpretation of this is that this new state will generate a representation of the dynamical variables, okay, a Hilbert space, but this new space will be orthogonal to the original one. Okay, there's some interesting points from this. Okay, each particular outcome has probability 0. Okay, each particular configuration of signs has probability 0. But of course, you can have sets of outcomes which have finite probability. For instance, all those which have the property that the first atom is in the up state. Okay. There are also sets of outcomes which have ill-defined probability. They're so-called Vitali sets. And almost all of the outcomes correspond to uncomputable maps from that family of sites to the sequence of signs. Now, this particular example suffers from what you might regard as a serious defect in that no finite observer could verify this change of representation with mathematical certainty, because our finite observer would be located at a particular event and her light cone would cut this initial surface in a compact region, which would include only finitely many of the atoms. On the other hand, it's true that later and later observers could acquire increasingly compelling evidence for the change in representation. Could there be, though, a circumstance in which the results of infinitely many different commuting measurements were known by one finite observer, say an observer at this event here in space-time? So if we don't have energetic restrictions on the measurement possibility, it's easy to come up with examples like this, because you can consider on a space-like hypersurface here, different families of different space-like separated field domains in which you might measure field properties. The field operators in all of these commute, so they're independent. And the results can at least be, in principle, be known at the vertex. Okay. On the other hand, as we travel down this space-like hypersurface, we need increasing boosts. So the energies involved presumably become unbounded. So this very simple idea doesn't work. But I want to just outline for you how you could construct at least in principle, something which looks like it does have a chance of requiring only finite energies and still measuring infinitely many commuting variables. Okay, so what I want to do is look at the S-wave sector of massless Klein-Gordon theory, which is just to make the problem simple and to take advantage of its two-point function, which is very easy to analyze. And the field operators there can be reduced to those of a two-dimensional field theory. And then it turns out that if you just consider averages of these at a fixed radius of over different time intervals, you can arrange for all of these to commute by taking sufficiently separated temporal intervals going back further and further in time. And presumably, because these extents can be made, very long in time for these field averages, the energetics can be made as small as possible. This is a very rough argument, but since we don't have a good theory of the energetics of quantum measurement, this is the best I can do at the moment. So using a construction like this, it's not very hard to contrive an example where we seem to be able to get infinitely many measurements, all knowable at one instant of time. Okay, so that's it. That's my talk.
Right, that's amazing. Thank you so much, Adam. Let's thank Adam for the talk. Are there any questions from the Zoom audience here? Okay, if not, then Adam, I'm not really sure how to understand the measurements and well the setup that you've described there in a relativistic setup, I guess. So would you mind speaking a few words about this? Saying a few words about this?
So the relativistic issue comes up in the question of causality, and related to that, the question of how much energetics, what energetics are needed for quantum measurement. So in this example here, although according to quantum theory, you have all these different observers making these different observations, and that's somehow happening all at this T equals constant hypersurface. It's not, that can't be known to any finite observer, because presumably the observer can only detect things in their causal past. So at any one point, maybe this really does happen in cosmology. Maybe there are these states that are created in one way and then undergo these measurements. At any one point, an observer looking backwards would see more and more of these states, which she might find are just always in this either in this particular pattern. Okay, and then you would get increasing evidence that the state had made a transition to this new Hilbert space, but you wouldn't know for sure because you'd only investigated at any one point finitely many degrees of freedom.
I see. No, that's amazing. Thanks a lot for the answer. So then let's thank Adam again. Sorry, Michael. Do you have a question or?
Yeah, I had a question.
Yeah, sure. Go ahead.
Yeah, about the spin model that you discussed.
Yeah.
You mentioned at the beginning of your discussion of it that you had a finite number of spins first, which you then made them all point down, and then I just wanted to understand: did you send the? Was it important in the argument that you have to send all the number of spins first all the way out to infinity? Then you do the measurements on all the spins, and then you get a state which is not orthogonal to the
number of spins. The number of spins is infinite from the beginning. This is in contrast to the way people.
Okay, I thought you mentioned that the number of spins was finite at the beginning, but maybe I misunderstood.
No. So it's actually essentially different from the way people usually think of infinite spin chains, where they think of a thermodynamic limit. This is a quantum system, and it's most plausible physically from a cosmological point of view. If you imagine that somehow the universe was created with this distribution of atoms, and for some reason their spins were mostly all one, their states were really mostly all of one sort. And then we imagine that later in the universe, some other measurement of the atom states is made.
I see. So I guess I'm interested in this from a condensed matter perspective,
yes,
where we might have 10 to the 23 spins. Is that like enough to be still like? I mean, it's still. Can I might as well consider that infinite and there be some effects there?
So in a practical sense, that might very well be more than enough, right? Just the way we are very happy to use canonical ensembles to describe things which are not actually infinite. To define you get into the question at some point of what are the other physical effects that are competing, and do they dominate the issues in the question of your system being really large versus infinite? Are the other physical effects so big that question is just not relevant to me?
Amazing. Thank you so much, Adam. Thanks for the question, Michael. So let's thank Adam again. Robert, do you also have a question?
Well, maybe there's not much time left. I just wanted to follow up on the relativistic question that what you think to having this problem of going to a different Hilbert space in the case where your measurement operator is compact in space-time?
That's a really good question. That gets into a very deep family of issues. That's the issue where the problems in change in representation are due not to infrared effects, but to ultraviolet ones. And it's bound up with the fact, with the notorious ultraviolet problems in quantum field theory, and I don't know what the answer, what the physically correct answer is.
Thanks.
Thanks.
All right, great. So now, yes, let's thank Adam again. And so, Adam, if you could, yeah, perfect. So Robert, if you could start screen sharing, that'll be great.
Okay.
That's amazing. I
Can
think
you see my screen?
Yes, we can see everything. We can see your mouse, the cursor.
Okay.
We can hear you as well. So I'll just introduce you. So our next speaker is Robert Oeckl, and he'll talk about hands-on with the positive formalism. So please, Robert, the floor is yours.
Thank you. So I just want to thank you, Rick, also for organizing this. And I think it's a very useful resource also from the point of view of having archived then later the talks. And okay, so let me start. So I'll tell you about the positive formalism. I guess many of you have heard about it. And here on this title slide, I put let's say what's really the main reference for the positive formalism. And I put it here also because the title of this paper does not contain the words positive or positive formalism. Okay, just a moment. Venimos a ver, es una plática ahora, ¿no? Ya está. Sí, perfecto. Gracias. Okay. Okay, I'm sorry about this. There was a problem with the electricity here. Okay, it seems to be fixed now. Okay, so yes, the positive formalism. So what is it? Okay, let me see if I can move this thing. Yeah, okay. So this is a predictive framework for physical theories, which is operational, probabilistic, and compositional. So what do I mean by this? Operational means that we have a primitive notion of measurement, of observation, of intervention. So instead of describing physics by saying, okay, we have a system, we have states, and now we want to see how they behave, the starting point here is the very notion of measurement, observation, or intervention. And everything else is secondary in the sense that it's built from this primitive notion in an indirect way. Probabilistic, so we are not, so we're going to predict outcomes of measurements and probabilities for them, and not make predictions that in general are certain. Okay, they are just, just probabilistic in general. Compositional means that we can talk about composing not systems, a system come later, but compose measurements, observation, and intervention. So we can say, so we measure this there, and then later something else here, and we are also switching a handle on this apparatus. And so we can compose all these notions together. So here, again, the primitive notion that encodes measurement, observation, or intervention, we call this a probe. This is basically the same notion that in other frameworks is called an operation or a process. Okay, so we'll use the word probe. So we also use the graphical representation of this framework, where the probes are represented as boxes. And here, the way I drew the boxes is to indicate that they correspond to some kind of measurement devices. Or for example, this one here corresponds to a switch. This is some kind of light that can have different colors, and this is a pointing device. And now, as I said already, the boxes here represent the probes. And what we can see here is a composition of 3 probes. And we can think of this composite as a single new probe. And it simply represents the joint measurement, or the joint action of all these 3 probes. So we have this instrument switched on A. We can see the green light on this other instrument, and the pointer points to a certain number here on this pointing device. And so in order to accomplish the composition, what we have connecting these probes, these boxes in the diagram, are links. And so the links indicate in which sense these probes, one way you can think about this is in which sense there are signals that can interchange between them, or communication between them, or an interaction. And then some more mathematical details. Let's say the links carry state spaces in which will connect later to what we know in quantum mechanics, for example, or in classical mechanics. The spaces of probes. So since we can put different probes in these boxes, we can talk about the spaces of probes. And of course, we also have the state spaces that I mentioned. And both of these types of spaces are partially ordered vector spaces. So they are vector spaces that carry a partial order. I'll say more about this later. And moreover, the mathematics behind this gives us a positive real number, or when I say positive, I mean non-negative, a non-negative real number, if we have a closed graph composed of probes and with these links. So one key aspect of the positive formalism is, of course, how do we predict with a positive formalism outcomes of measurements or observations. And to do this, what we need is not just one of these graphs or diagrams, as we've seen on the previous slide, but in fact, we have to think about 2 copies of those, because when we ask for a probability for something to happen, we have to specify what we already know about our system. So for example, in this case, what we know already is that we have these 3 apparatuses, and moreover, that this one here is the switches in position A. And the probability will be really the probability that what happens is what's indicated in the probes on the left-hand side, conditional on having the probes on the right-hand side. And so unsurprisingly, this probability will be a quotient. As I said already, each of these diagrams, when they're closed, of these graphs, gives a number. So it's simply the quotient between these two numbers. So it's this will be the numerator, the question which encodes the question we are asking, and the denominator encodes what we already know. And here, so these diamonds are just a symbol to symbolize this composition without talking about these links explicitly. Now, there are different versions of the positive formalism. What I've told you so far is what can also be called the abstract positive formalism, where you can connect probes arbitrarily with each other. And so you just have a graph. Now, what you usually do, and for example, that's the case of quantum mechanics or also classical mechanics, you add a notion of time, and that allows you to talk about time direction of these links. And what you get is a directed acyclic graph or directed acyclic graphs. Now, there's another important ingredient that you use, for example, in the standard formulation of quantum theory that I'll mention later. You add a causality axiom. This gives you the same kind of graphs, but what it means is that you impose certain restrictions on what kind of probes are allowed. And when you do this, your probability rules simplify. So in particular, this kind of probability rule, if you're talking about a measurement where at the end of the measurement you're discarding, and on the right-hand side here, what you're conditioning on consists only of non-selective probes, then this denominator is 1, and you recover a probability rule that just looks linear. Okay, so I mentioned a little bit, I made some allusions to quantum theory, but I didn't really say that I was talking about quantum theory, and in fact, I wasn't. The main mathematical structure that I mentioned is that of partially ordered vector space, and in particular, these state spaces that I mentioned are partially ordered vector spaces. And it turns out they are not all the same. So if you just have, for example, a finite dimensional partially ordered vector space of a certain dimension, it will not be isomorphic in general to another one of the same dimension, but they are different types. So what are the types? So one type is called a lattice, and what happens there? Well, the state space in this case is the algebra of functions on a set. And that set is nothing else but what we usually think of as the phase space. And these functions are just statistical distributions on phase space. And basically, in this situation where the state spaces are of this type, what you can describe, for example, is statistical mechanics. And more particularly, this happens. So the framework you're in statistical mechanics is the positive formalism, this classical version, where you have a notion of time and you also have this causality axiom. Now, there's a kind of other extreme case, which is to the lattice case, which is the anti-lattice case, where this state space is basically the space of self-adjoint operators on some complex Hilbert space. And this is exactly the case where you get quantum theory. And indeed, the standard formulation of quantum theory is precisely the positive formalism in the quantum case with a notion of time, of directedness, and the causality axiom. And you recover exactly the standard formulation of quantum theory. Now you can have other situations where you don't have neither lattice nor anti-lattice, and this is then you have basically generalized probabilistic theories that are of some interest in the foundations of quantum theory people are interested in that, and they are usually formulated in what corresponds to the in a formulation that corresponds to the positive formalism plus time plus causality axiom. Now, an example here of an application. Well, this application is the indefinite causal structure, and this is a work of Oeckl, Costa, and Bruckner from 2011, a seminal work, where they describe a situation where you have two laboratories, but you weaken some of the rules of quantum theory. And in particular, you can think of this in terms of what I was telling you as three probes, two of them laboratories, and one that describes how they interact with each other. And now you allow this interaction, which so in their formulation, it's called the process matrix, to not obey all the axioms of quantum mechanics. In particular, you are removing this causality axiom and also the acyclic directive ordering axiom. So I'm just putting this example here to say that this fits completely natural in the positive formalism and can be described in this way. And now, other directions of applications. I was, in fact, I didn't go much here on when I was on this slide. I didn't go into details about this version of the positive formalism. What you do here is you think of the probes as localized in space-time, and so you make a diagram that corresponds to space-time or to a division of space-time into regions with interfacing hypersurfaces, like here. And so now in each region you have a probe, and the interaction, what I draw before as a link corresponds to the hypersurface that interfaces these two regions. So this is the setting that's in fact relevant for quantum field theory and for quantum gravity, which I'll say a little bit more about in a moment. This is also the setting. There's a pure state version of this, which is called the general boundary formulation, which has existed much longer than the positive formalism and has been used in particular in spin-form quantum gravity quite extensively already for quite some time. Here another example from quantum gravity, black hole bounds. It's an extremely simple model that just has two parameters where a black hole transitions to white hole, so because of some quantum gravitational effects. And in terms of the positive formalism, you just have two probes here. One is the quantum evolution in the interior of the black hole, and the other one is a classical space-time where you make a measurement. So you have an observer that sees a mass shell collapsing to a black hole, then it bounces to white hole, and at a later time the observer sees the shell coming back and can measure the time and can infer something about the exterior geometry. There's a one parameter family of these geometries parameterized by the bounce time, and then can use that if he knows how this quantum theory of gravity works, predict the bounce time. What I want to draw attention to here is that there's no definite temporal order between these two probes. So this happens at the same time. So this is why with the usual formulation of quantum theory, this is problematic and cannot really be treated. But with the positive formalism, that's perfectly treatable. So that's a paper 2018 about that. Another example, Rick, can you tell me how much time I have left, just to be, sorry. Okay, so here's an example from quantum field theory. The S matrix is where you have some initial state. separated particles, then you have some interaction, and at a later time you make a measurement and see what are the particles that come out. So this is usually done in a time interval setting. So you think of this initial state being at very early time, the final state at very late time. But it turns out that, I mean, using the positive formalism, you can do this in a quite different way and have different types of geometries. So in particular, you can think of a sphere, having your experiment in a sphere, and you shoot in particles and they come out and you detect them on a detector. So this is quite close to how actual experiments actually work. And so you model this by this hypercylinder, which is the sphere extended over all of time. And you have particles going in and coming out there. And you have a Hilbert space of particles associated with the boundary. And then you can calculate the amplitude, and you can calculate scattering probabilities using the positive formalism. And the advantage of this, for example, this also works in ADS, where the usual S matrix doesn't work. And another application that we've recently focused on is that you can use this to describe the interaction of evanescent particles with an Unruh-Dewitt detector. So anyway, I'll say more about this. Somebody asks me. So okay, I'm coming to the end of this small presentation. Here's just a little presentation of our group here in Morelia. Working in particular with Daniele Colosi from the NS, also here in Morelia. Adamantia Sampelli, she was a postdoc here. She just went to ICTQT at Gdansk. We're working on measurement in quantum field theory. With Daniele, we are working on these evanescent particles, the time of arrival problem. Juan Daine, he was a postdoc. We're working on a categorical formulation of the positive formalism. Mario Molina, he just graduated. He got his master's thesis graduated just the day before yesterday. Okay, so let me just say, so we have opportunities here for people to join on different levels, PhD, postdoc in particular, also masters, and yeah. So thank you for listening.
Amazing. Thank you, Robert. So are there any questions from the Zoom audience here, from the Zoom spectators? Because if not, you kind of gave me gave a preview of the question that I wanted to ask, which is whether there is any relationship between this framework for thinking about measurements and Unruh-Dewitt detectors. And you said that you had some sort of idea regarding evanescent particles and things like this. So
yeah, thanks for asking. In fact, I didn't have time to talk about it, but there's we put out a paper about this just recently, so you can find it on the archive. It's about I think it's called something like interaction of evanescent particles with an Unruh-Dewitt detector. And so basically, if you look at this picture here, you can think of this as putting in the middle of the sphere in space, you put your Unruh-Dewitt detector in the middle, and you let it interact with particles that you shoot in or that come out. In the simplest case, you just look at a single particle or so these evanescent particles are basically arise in the near field, for example, of electromagnetism. We studied them in the context of Klein-Gordon theory, and there they arise if you have a mass, if the field is massive. And you don't see them in the standard S-matrix formalism. They're invisible there because at infinity, they decay exponentially. But if you're at finite distance, you can see them. And you can ask the question, do they also interact with an Unruh-Dewitt detector? Are they like ordinary propagating particles? Can they excite an Unruh-Dewitt detector? Can they be emitted? And it turns out the answer is yes. So have a look at that paper, which I didn't put the reference here because this slide isn't up to date. Sorry about that. You can find it on the archive. Thanks.
That's amazing. Thank you so much, Robert. Let's thank Robert Oeckl again. So, yeah, that's perfect. I would just like to say a couple of words to well end this series of conferences. It's been a pleasure to travel through many places and to help. Well, I don't know, like bring the community together and to really interact. Every single minute that I spent interacting with people from this community and talking about research, talking about well everything else that we talked about throughout this whole time, it was a great experience. And also thanks to all of the online speakers. It's been a pleasure to also have these amazing talks for the past 2 weeks, and I think it's a good thing to be able to well bring you guys together. Although either there's no big group that is able to host a local conference that we're gonna do whatever, but it's nice to have everything here, and I can definitely. Well, I'm so grateful to this RQI community, and I can definitely say that I really I really like this. I really like every single person that has been a part of this, that wants to be a part of this, and I like doing this kind of job. So I'd like to thank everyone that somehow supported, somehow said something, some positive comment about the circuit, anything like this. Every little bit helped. Every single talk helped a lot. We had a lot of engagement. We had more than 2,000 views on YouTube. We had a bunch of talks. We had over 100 talks. It's been nice to see how easy it is to bring this community together simply because well it's already there and it's been flourishing for a while. So yeah, I'd like to thank everyone. If you're watching on YouTube, thank you so much. I'll stop the streaming now. I don't know. And it's been a pleasure again. So thank you.